Hello, everyone. I know it's written that we're going to start at 9 a.m., but we are in advance on our schedule being late. So we're going to start now. Very happy to see you. Very happy to see computer vision people also in an NLP conference. So I know this is a pun, actually, right? It's not supposed to be an NLP conference, so it's supposed to be on AI in general. So today we're going to have the weekly supervised computer vision workshop, and for those that were around in the last year, it's actually our third edition. Let me try to click. Yep, okay. So it's actually our third edition. I did not present myself. I'm Raoul de Charette. I'm a researcher at INRIA. And as I said, third edition of the weekly supervised computer vision workshop. We're in the big auditorium, so as you can see, it's very, very big for our audience on computer vision. So don't hesitate to really locate in the center for our speakers to see you during the talk. So this year, as in the previous year, we have a fantastic lineup of speakers. Ranging from academia to industry, working on different continents, some people that you know from the African continent, some from Europe, America, etc. And there was the link before for the program, so you can access the agenda, the exact agenda of the workshop, but I just want to name them really quickly. So we have Vicky Calogueton from École Polytechnique, Daniel Omeza from Oxford that actually just moved in US, Joyce Nakatumba Nabende from the Makerere University in Uganda, Oriane Simeoni, that's going to be our first speakers here, from Valeo AI, but I'll detail that. Candace from Meta, Daniel Adjisafe from the University of British Columbia, and Pierluigi Zama Ramirez, that is already there. It's going to be the second speakers from University of Bologna. So fantastic lineup of speakers and a few change compared to the previous workshops in the last year. So you'll see that. So what about the agenda? This is the agenda, so times have little shifted, but this is the general agenda. In the morning, we're going to have 4 talks, starting with Oriane, then Pierluigi, Daniel, and Candace. I didn't say anything about the topic, but we're going to be revolving on all visual data, so it can be processing of images, processing of 3D data, but you'll see that NLP has also submerged, I would say, the field. So you'll hear probably quite a lot of image and text alignment, 3D alignment, multimodal processing of model, and how to train this kind of thing. And in the afternoon, so we'll have 2 other speakers, Daniel and Vicky, to close the session. In the middle, we'll have spotlight presentation and poster session. So we have 20 posters on computer vision that will be set up during lunch time. And at the end of the day, there will be a panel discussion and announcements of the awards of the workshop. So you'll see the speakers will be also the judge for the awards, so be nice with them. And one thing that is a change compared to the previous edition is that at the lunch break, we will have also a mentoring lunch. So what is the mentoring lunch? It's actually an opportunity for you to discuss in small group with the speakers. So the idea is that if you want to subscribe to the mentoring lunch, you have to fill that form. It takes 2 seconds. You just have to put your name and which speaker you would like to be assigned to, let's say. And this is, we see that as a unique opportunity also for you to discuss with top-tier researcher from all over the planet, and being able to discuss any of your idea that you have with them, share your problem, can be even technical problem, you can really use them. So it's not going to be a break for them, but for you, use that as a time to interact with them. So just register on the form, and we'll try to solve this assignment problem during the talks. Okay, and I'll show the slide again for those that didn't have time to scan it. I'll show it during the break, the coffee break. So beside mentor, I said that there will be an awards. So two sponsors for the awards. GoPro on the right with a Hero 13 to win, and on the snap on the left is not exactly the amount of money that is being visible on the on the gift, but close, 500. So that's about it. A quick thanks for all the organizers that you can see there. Fabio is also there on site, the other are not, but and especially I would like you to give a round of applause for our volunteers that are in the room or elsewhere. So our volunteer will be around, and you can ask them questions about the workshop. You'll see them roaming in the room. And finally, before I give the floor to Oriane, I want to highlight one thing. With other researchers, we started, and I think it's key to highlight in this workshop. So we started the first African Computer Vision Summer School, which had its inaugural edition in Kenya this year. I want to highlight that. It's not really the topic today, but I think if you're interested by computer vision, if you're from Africa, you'll be interested by this summer school. I want to say a few words. So it happened the first time July in Nairobi, Kenya. We're about 10 organizers. You don't see us there, but there you have organizers from all over the world also. And basically, ACVSS is an immersive summer school. So it's 10 immersive days where speakers, organizers, and participants stay together in the same hotel. This year was 17 speakers that you can see on the right. You're going to spot some very big names also, and only quality speakers. And the summer school was a mix of lecture, practicals, keynotes, everything included. And I want to highlight that this year we funded absolutely all participants, actually all but one that said that they wanted to pay for their own flight and accommodation. But this is, last year we managed, or at least this year we managed to make it fully covered. So we were taking in charge everything. So if you're interested by next year edition, check our website. I want to highlight also Twitter, of course, but also the YouTube. If you go on the YouTube, you'll see that we have already posted all the keynotes from this year, so you can have an access to that. Next edition is going to be in summer 25. We don't know where. So the idea is to unite talented African students with the top tier computer vision researcher from all over the world. And we're going to share the call for participants probably around spring. We don't know where it's going to be the next year edition, but on the continent for sure. Okay, with that, I'll close my introduction remark. I'll give the floor to Oriane. Oriane is, so as I said, our first speakers. A few words, yeah, you can disconnect and reconnect. First speaker, she's currently, I should say, in Valeo AI, which is a company working on fundamental artificial intelligence research for autonomous driving field. And she's actually on the moving right now. She's right in between the two jobs because she's moving to Meta in a couple of days, actually. And Oriane is working on computer vision and especially algorithm that requires little or no human annotation. And she's been working in the past in RIA Rennes and now also with Twitter, right? Yeah, internship at Twitter and Google, right? I was surprised of seeing Twitter for computer vision. Okay, so let's welcome Oriane, please. And thanks a lot, Oriane, for being there. We're very happy to have you with us today.
Thanks a lot, Raoul, and thanks for having me here. I'm very excited. Very excited to talk about a subject that is quite dear to me. So today I will talk to you about object localization almost for free, harnessing self-supervised features. Okay, so let's dive into it. So I guess if you are in this room, you probably know why we care about object localization. But today there are many systems which are on your smartphone, which are systems that are like self-driving cars, which require to detect the object in images. So for instance, if you want to do some smart filtering of a person from the background, if you want to zoom nicely on the people and have the more higher resolution on the person than on the background, you want to do object localization. If now you have a system which has to interact with a scene, like on a self-driving car on the road, or a robot handling objects, then you want to find where are the objects, and also you might want to know what are the objects. So I think this topic is very interesting. It's been tackled for a very long time now. But I will say until a couple of years ago, it was tackled with benchmarks that probably you know, Pascal Voc, COCO, which are benchmarks which have been defined with a certain number of classes. So 20 for Pascal Voc, 80 for COCO. And for each of those classes, people have annotated a lot of images, which takes time and costs money. And basically, it's quite limited, right? If you think of a system that you want to interact with the world, if you have 20, 80 classings, that's not enough. So that's the first problem that I think we had with the classic benchmarks. Another problem that you might think of is that better models have been trained in a fully supervised training fashion. And that means that you need annotation for each of your classes. That's expensive in terms of money. I think if you know about annotation process, it's also expensive in time. It requires a lot of time to well define the problem, to define how you want the annotation. So it's very time cumbersome. Then another problem is that if you want a new class, well, you have to start again. You have to get the annotation, define it, and then you have to retrain your model. And that's very slow and very long. So for instance, if you think of self-driving cars, in Paris, I don't know, I haven't seen many in Dakar, but suddenly on the road, there were scooters. Those like, trottinette in French, scooter in English. Yeah. And basically, you want your car to know how to interact with the scooter because they go actually really fast, and you will want to know that it is a scooter. But so then you have to re-annotate, retrain, so it's very time cumbersome. If you think of a way to handle the problem of not caring about classes, you might think of the work SAM. So I guess most of you know about Segment Anything, which was, I think, 2023, like in March or something, was published. And it's dragged a lot of attention because now suddenly in this work, we don't care about objects. All of the objects are annotated, are discovered by a SAM model. So that's great. You can click on your image and have masks which will discover all of the objects. However, this has been done at the cost of a lot of annotation. Large collection of annotated images had to be gathered. So it's 11 million of images that were annotated with 1.1 billion masks. They were not all made by human. There was a more interactive process, but still very slow and very expensive. Also very expensive to train your model on that, because you need to go through the 11 million images. Okay, so now what I want to focus on today is try to find a way to understand our complex world in a more, with less boundaries, basically. So we might want to interact with new objects, as I said, weird objects. And one question that I wondered about is, what can we do without human-made annotation? Can we avoid altogether having to go through a human that will annotate an image 1 pixel at a time? What can we do? And can we also avoid having to do this process of a new class? What can we do that will be class agnostic? So today the talk will be about how to find and perceive objects without knowing anything about them. Big question. So let's start. So I will have 3 parts in the presentation. So I will tackle unsupervised object localization. Here the problem we are going to discuss is only in images. I haven't worked on videos, but you can transfer, I think, quite easily from image to video. And the idea is that we have no information, no supervision about objects available. And the first project I will talk to you about is about unsupervised object discovery, where we are trying to find at least one object in the image. The second work will be about foreground-background segmentation, where you want to separate the foreground from the background, again with no annotation. And the last one, which maybe is of high interest today, is, okay, if we have things without annotation, how can we get annotation for free almost? And then we will discuss about zero-shot open vocabulary semantic segmentation. Okay, let's start. So I don't know if you noticed in my title, there is harnessing self-supervised features. They are really at the center of a lot of my work. And just to remind ourselves what self-supervised learning is, it's the idea to use a proxy task to train a model to learn features that could represent an image. So for instance, one of the first works that did it successfully is RotNet. And the idea is very simple. Your task is going to learn to predict the angle to which you have rotated the image. Because you do the rotation, you know the angle, so you have the annotation for free. And learning this task allowed the authors to get really good representation that can then be used for classification. Since then, there have been really a lot of works on self-supervised learning, Deep Cluster, MoCo, MAE, Dino. I guess you might know of a few of them. And they all have shown that self-supervision is very powerful to pre-train models, to do fine-tuning, for instance, to adapt for later tasks. And it's also shown that the properties of localization are quite good. So here I will focus on Dino quite a lot in the presentation because it worked very well with Dino, but their concepts can also be adapted to different features. So why Dino and what is Dino first? So Dino is a self-supervised training technique, which is very simple. You have one image, you take 2 crops in your image, you feed them to 2 models, a student and a teacher, which are the same models, and there is an exponential moving average relation between them, sorry. So you feed them 2 different crops of the same image. You take predictions on the outside. Here there are, I think, 700 classes. They don't mean anything. They don't correspond to anything. And your objective is to have those 2 distribution of classes to match. What you hope is that the student and the teacher with different versions of the image will predict the same class prediction at the end. That's it. And that has worked really well. Surprisingly, they have shown that it's very good for classification, reaching at least as good result on some tasks. So very exciting. And when I saw, so that's the first page of the paper. And I saw this paper was, I think, in May or April 2021. And I was already interested in object localization with little supervision. I saw this paper and I thought, okay, are we done here? I can see the giraffes, I can see the dog, I can see the airplane. It's very obvious that with just self-supervised learning features, they have managed to find the objects. So I was kind of wondering, are we done? Have they solved the whole task? Well, obviously it's a bit more tricky than that. So if you think of what those maps are the self-attention produced in the last layer of the transformer model, and they are corresponding to the CLS. You have 6 heads in the model, which are all doing something slightly different. So you have 6 maps like that. And when I played with the model, just to try and understand what it was doing, I got this on like a bit harder images. These are the self-attention maps of the different heads. And as you can see, they kind of focus on the objects, but it's not very clear. You can see that sometimes the dog and the person are highlighted, but sometimes it's blurry. And so when images are a bit more complex, it was not obvious to use them straight away. So that's great, because that gives me work to do. There is something to be done. And so that will lead to the first work I will present today, that is called Lost, that will tackle single object localization. So just before presenting Lost, one thing that I will use a lot is the construction of a graph. I took that slide from a tutorial I made at CVPR, so if you want more details, you got them here. You got them there, on YouTube actually. But so the idea is that you have your input image. With a transformer, you have patches on the image that are fed to the self-supervised backbone, which is frozen. We don't touch it. Then you get your tensor at the end, 1 feature per patch. So I've represented that there. And when you consider the feature space, so here it's in 3D, but the features are 512. So you imagine actually much larger space. But let's say if you look in the feature space, you obtain this graph where one node is 1 patch. And we connect the different nodes with edges that are based on the similarity, cosine similarity. So just the dot product between the features. And doing so, we are able to obtain a graph, we just connect the one that are above a threshold. So it's a sparser graph. And we also binarize it. Do the node have a similarity above a threshold or not? In most of the work, it's 0. So is it positive similarity or is it not? If it's positive similarity, it means the nodes are similar. And yes. So what we observed in the work is that the space is very interesting. It's very well organized. So here, obviously, it's a representation, but if you look in the space, you will find that all of the patches of the sky are very close, high similarity between them. Same thing we observed for the rocks. The texture is the same. All of the patches of the rocks have a high similarity. And the objects are somehow correlated, but with more information to it. And that's what we are going to exploit here. So for our first work, single object localization, we have our backbone. We actually take in the last layer the key features, which were the best features, and we build our similarity graph like I've shown you just now. And what we observed is that the patches of the foreground are less correlated than those of the background. What does it mean? It means that here, the patches of the background are very tight. They are very close in the space, high similarity between them. When actually the patches of the foreground, the features contain more discriminative properties, and each patch is a bit more different. There is more texture, right? If you think of a person, then you have the face, which is quite different from the pants. And so that's really meant that we have this distinction between foreground and background. And here is represented the patch degree. The degree of a vertex of a node in a graph is just the number of edges that is connected to that node. So if you think here, for instance, the top one has a degree of 2. So that's very simple metric. And here we just represented the degree. So the lower degree is in yellow and the higher degree is in blue. And I don't know if you can see, but like basically all of the patches of the background are dark blue, and which means that they are highly correlated to each other's. So, and I don't know if you can already see, but we see the objects, right? Here we really see them, okay? And then we had an idea, which is, well, what about the object? Well, let's start with the patch with the lower degree, the smallest degree. So it's the red dot. I don't know if you can see well. So for instance, on the bird, it's on the face of the bird. And if you take the patch with the lower degree, then that's what you get. And so it's great because every time it's on the object. And then we looked at the similarity to the other patches, and there you go. You got your mask, right? It's here. We have the boat, we have the bird, we have the horse. Obviously, it's missing some patches, but basically, we obtain our objects already. So that was what we did. Very simple method that runs in 60 frames per second, and we obtained those results with that method. So here you can see that the persons are well detected. You can see that the head of the cat, which I find pretty cute, is well detected. The racket of the tennis player. And so you can't really control what object is going to be detected. It's likely to be the smallest one or the most discriminative one. But even the tennis player on the court, which is very small. So that's the result that we got with a method which is very simple. You just construct a graph which takes very little time with your image patches, and then you find the least connected patch, and you find the similar patches to that one, and that's your object. So in terms of results, basically, at the time, it was really, I was really surprised, happily surprised. We improved over previous baseline by a lot. And I didn't really talk about the previous baselines, but what they did would be something much more expensive. They will look at the whole data set, and they will connect images of the data set and try to find recurring pattern. So that's very expensive because it depends on your number of images in your data set. And also it requires for you to connect all of them, so it's quadratic. So they were very expensive. And we have a very simple method that runs at 60 frames per second with self-supervised features, we reach those results. So we were very impressed. And then obviously that's not enough, right? One object in your image, you want more than that. We want to go to multi-objects. So we thought about it, and what we thought of was, well, we have a method that is producing one box per image. How about we use that as our ground truth? So we use the predicted box we've lost as our pseudo labels. And we called it plus CAD, which is a class agnostic detector. We trained a model. Here, it's faster as CNN. We took it as it was. No adaptation, we didn't have time anyway for adaptation, so we just took the model and we trained it with the pseudo box that we got from Lost. So in Lost, we have one box per image. And we were extremely excited to see that not only the detector improves the results on the core lock metric, which is the one we had before, but also the detector is able to go to multi-object detection. And so you are now with the detector, because it has learned to detect objects in a class agnostic fashion, you can detect several objects. Maybe one thing that I didn't say is that in our detector here, we have only one class. It's object. Because then it's class agnostic, we don't care about which classes, and we obtain really exciting results. I didn't put any result here, but it was good. So since then, more powerful algorithms have come out to do basically what Loss did, but better, a bit slower maybe. So you have token cuts that you might have heard of, distributor method, self-mask. So they were using the same features, very similar graph. The only thing that they did was to use a graph cut solution with spectral clustering, and they improved the localization. The borders are better, and the objects are more better detected. Still here, it's single object discovery. Maybe you also have heard of Cutler, which was CVPR23. And in Cutler, they detect several objects. So I'm talking about the Cutler, the mask cut, I think it's called, which is they repeat the process. So they detect in the graph one object, they remove the nodes corresponding to that object, and they go again to detect a second and a third. So they have showed that they obtain interesting results by just doing this repetition. They have some heuristic to say what is an object, what is not. And I think 3 was probably because it worked well. Why not more, why not less, I'm not sure. But in any case, it's a method that showed that you can go to multi-object with already just the graph. Then they also have a training phase, but that's different story. And yes, we worked on a survey that is now accepted at IGCV, which kind of summarize all of those methods and how you can use self-supervised features to do unsupervised object discovery. Okay, now going to our second problem, which I talked to you about, which is foreground-background segmentation. Here it's slightly different, but still using the same features. So we still have our image, we still have our self-supervised features, backbone that is frozen. We have our keys because they work well. And in this project, we were thinking of, okay, we are looking for the object. We know nothing about the object, but what we know is that there is some background, and we've seen in the previous work that we can detect the background very well. So if I find the background, what is not background are my objects, right? What is not background, the complement of the background are the objects. And that was the very simple idea that worked well to discover foreground. So we make no hypothesis about the number of objects. We don't care. We don't care about the object. We just care that there is a background and there are objects. And so what we did was, well, how do we find this background in a better way? One thing that worked really well was to take the attention maps that I showed you at the beginning and to take the patch with the least attention. Simple. We just concatenate, I think we averaged all of the attention maps over the head, and we take the patch with the lower attention score. Well, that's it. We have our background seed. And now what we did was to find what was similar to this patch in the image. And that's how we got our background mask. As you can see, it works pretty well. So there, it's a bit noisy. It has pixeled on the flower, but more or less, it's doing a very good job. And this is results on other images where you have one object, the lion, for instance. Here we have several objects. We have the boat, and I don't know if you can see, but it's building in the back, which are also not detecting in the background. We have the person on the boat with the umbrella, and the background is very well detected, but the person is not. So great, we are doing what we want. And one thing that we thought of was, okay, so we have our background, so we can use that to generate the foreground. And so that's good, we can do our algorithm to find that, but we want to improve this because we saw it's not very good. And what we observed is that you can obtain extremely good results with learning one layer on top of the self-supervised features, only one. It's a convolutional one layer, the cheapest we have. And so what we did was, okay, we have our background mask. We're going to use that again as pseudo-labels. The same system as before. We have our ground truths that we have generated. And now we are going to learn, the model is going to learn with a convolutional 1-1 on top of the K features to make the same prediction. So it's binary. Is it foreground or not? And we use what we predicted at the top for annotation. And well, we observed that it works well. One thing that we did as well to improve that was to add a step of bilateral solver on top of the masks. And bilateral solver is an older technique, which role is to basically improve the edges of a mask using the pixel. Because in the pixel, you have the information of the colors, right? So you kind of know the boundaries of the flower. It's very easy. If you go back to computer vision methods, they can detect those boundaries very well. And bilateral solver is doing the job of, you have your mask, and it's improving the boundaries on top of it, and it's working well. And so with that, we train our conv1-1. I think the training takes 1 hour on one GPU. We train on 10,000 images. And these are results that we obtain. What I really liked about those results is that we threw in some random images, dinosaur with a person, what is maybe a UVO, I don't even know myself what it is, but somehow the model, because it doesn't care about classes, doesn't care about what are the objects what we need to detect, detects it very well. Here you have an example with a cow and people running, and rather small object, and it still is able to detect it. Football players, and then this, I don't know where it is, a bicycle with a dinosaur, I don't know. But in any case, the model, because it has no assumption about the object, was able to detect it. Another thing that was really interesting is that the method ran at 80 frames per second, because it's dyno, which is very quick, and it's one conv1-1, that's it. Nothing else. So you can, it's not the most perfect result. They could surely be improved, but we really were able to, you can use that for videos with quite a good accuracy. And so no, the training was 2 hours, sorry, on a single GPU. So 10,000 images that have no annotation. We don't care about annotation because we are generating our own pseudo annotation. In terms of, in terms of results, maybe it's too small. In any case, we obtained very good results. They were better than some of the methods with and without training that were before, okay. But I think the thing that we were the most excited about is that the method is very light, both for training, both for inference. It has less than 1,000 learned parameters. So that's it. So now we've seen that we can detect foreground and background with, again, our self-supervised features, no annotation. So that's great. But the problem that we want to tackle is a bit more open than that. We want classes, right? We care about knowing what are the objects that are in our world. We want to go a bit further. And so what about classes? And this is the last work that I will present to you today, which is called Clip Denoiser, and which, again, surprise, uses self-supervised features, but this time with clip, and generates good open vocabulary segmentation. So how do we do this? So I guess most of you are familiar with clip, but I will go over it again. So clip is a model that has been trained to align text and images. So the text was obtained in a very weak fashion. You just get data from internet, that you get the metadata, etc., and you have text. And in the model, it's a contrastive learning-based method that really try to align the image features and the text features. You have one descriptor per image, one descriptor per text, and that's it. And that's how they trained. And so the data, so it was a long training, I guess, but the data is very cheap to obtain. It's basically the internet. And what they observed is that Clip is very good in saying there is a ship. Okay, so you can throw in whatever prompts you want, and you find the one with the higher similarity at the end. You have a dot product between the text embedding and the image embedding, and you can classify your image very easily. So it's very powerful. However, there is a however. How do we go to the image level? Here it's very good for classification, but here we care about segmentation. We want to know more than one object, and we want to know where they are, how we do this. So there are several methods that have done some training, adaptive training, to try and do this task with some success. And there are some other methods with no training, but obtain quite noisy results, mass clip, that I will talk to you now. But obviously, now you realize how I'm thinking. I know that self-supervised features are very good at detecting objects, aligning object features. So any way to leverage that to go from clip to object localization with classes. And that's what we will do now. So we started from mass clip. So mass clip, why? Because mass clip is very light, very nice to use. You have your clip backbone, it's frozen. You have the same clip text backbone, also frozen. And there is this one layer, which is not trained. It's basically just, you drop the last global pooling, and you're going to transform what was a fully connected layer into a conv1-1. That's it. So basically, you don't have a global pooling at the end anymore to generate your image embedding. Now you have patch level features, and you have the last layer that was on the global embedding on the patch features. And so that's what they got, that's what they did. And so that's really nice, because now you can go to the image level. So you can compare each of the words to each of the patches. And they obtain such types of maps. So pretty good. And as you can see, very noisy. So we need to improve that. And that's where self-supervised features come to the rescue. Because we know that correlation is very good in self-supervised features. So if you see, for instance, your map, correlation map, you put a dot on the sofa, you know that similar patches are around this area. And as you can see, it's pretty well segmented. And what we have done, what we have thought of, is we're going to use that to refine mass clip results. And so what we did was to propose a guided pooling. And the idea is very simple, is that you find, for each of the patch, you find what are similar patches in self-supervised features, and you do a weighted average. The weight are your similarities. That's it. And so doing that, well, we obtain that. So the plant, in bright green, it's the plant. You have the sofa. You have the table in blue. You have a lamp in purple. And in the back, I think it's window and wood, I think, or I can't see. In any case, so we really refined with the self-supervised features, mass clip result, and obtained something that is much more close to reality and to something that is usable. And now the next step is, well, that's great, but could we learn that? Because I don't want to have to use two backbones every time I want to apply my method. I would love to use only clip. And what we observed is that if you train this time a conv33 with a binary cross-entropy loss to produce the same correlation map that you have with Dino features, then you can obtain the same result from clip. And here the training was of 40 minutes on NVIDIA 85000, and the training is done on 1,500 images. That's it. You don't need more. The images are not annotated. And what we observed that with training, I don't know if you can see, but you use clip features, you have your COM33, and with training, slowly, you can see the similarity appearing. And in the end, we were able to exploit clip to have the same quality of representation, similarity prediction than Dino, sorry. So what we understood from that is that clip already contained very good localization properties. The model, throughout its training, although it's been trained with global objective, it has learned about pixels, about what objects, how they are connected, and we just need to extract it. And then we can apply, again, with our newly generated maps, we can apply our guided pooling, and we obtain the same result as before. The paper is entitled Clip Denoiser, Teaching Clip a Few Dino Tricks. There are only 2, actually. But what is the second one? Obviously, if you think of the second work I presented to you, where we can predict foreground, background from clip, well, I was wondering, can we do the same thing with, from Dino, sorry? I wondered, can we do the same thing from clip? And we tried, and it works. Because clip also has very good localization properties. So basically the same way that we train the conv33, we will train a conv11, which role will be to predict the binary foreground-background segmentation that we got from found, the previous method. Also trained with binary cross-entropy loss. And doing that, we can go from a map which was a bit blurry to a map which really discards the background, which you might want in certain cases. So here the prompts are train, dog, and background in black. And so if you have that and you use the conv11, then you can obtain a more refined map. So we were very happy with those results. You can see, so you have the image on cityscapes, which is, I don't know if you can see a street. Then you have the ground truth with the cars in the back. Our result, which kind of detect very well the cars in the back. And we obtained good result compared to previous works. And so we were very, very happy about that. And again, the interest of our method is that it's very cheap. You only train a conv33 and a conv11 on top of clip. That's it. And so when you go at inference, it's very quick to use. And so here are some more results where you have the ground truth mass clip, so where we start from. Then you have ours after the guided pooling. And as you can see, it really helped in removing all of the noise, all of the hallucinations. And here we threw in we have our classes, so you have in datasets, in the prompt, you have 20 classes or more, or 80 that are thrown in. And with our method, we can really clear the noise. And it can work on video because, and here we have no consistency rule. One frame to another, we apply our method separately. And what we observed is it's quite robust to the small changes that you have in the video. So we were pleased about that. So more qualitative results, this time with more random prompts. So we have big dog and small dog, which only clip can do, this type of annotation. And although it's not exactly perfect, at the end we are able to reach, it's missing the feet for some reason, but on the dogs we are able to clean the map and really have this big dog, small dog result. Then on a painting, which has never been seen by clip, I think, you have a dancer and you have, we put in red, no, it's in orange, impressionism. I was driver, no, there is no driver. But you have impressionism, which, I mean, even to me, I would not be sure of where to annotate that. But it's in the back because it's the type of strokes that were on the painting that correspond to impressionism. But so results that you basically, that for me were quite striking. You can really use clip as it is to do object segmentation. And one last one, I think this one is quite funny, with Princess Leia and Ada Lovelace, and then basically the hair. So this is actually Ada, but the hair is more like Princess Leia in Star Wars. So funny stuff can happen. Obviously, we don't control that. But then if you look for rusted van, you have your rusted van. If you look on your image for white horse and dark horse, then you can annotate both of them separately. You can put prompts that are quite accurate and obtain fairly good results. French pastries will be the croissant and the pain au chocolat. Yeah, so those are the results that we obtained, so we were very pleased about it. And this is the last work that I wanted to talk to you about. There is the literature on this type of works in the last 6 months has increased a lot, because I think we all realize that we want to get out of the class-defined benchmarks, and we actually need new benchmarks that will not be Pascal, Coco, because those are very limited, and right now this is how we evaluate, and it's really limited to, can I detect a car, can I detect a person, but what about I want to detect the white horse and the dark horse, how do I evaluate that? And so basically, yeah, I think the community needs to think of where do we go from now? What benchmark can we build that will actually help us in evaluating correctly open vocabulary semantic segmentation? Because I don't know about you, but I think this is a direction that we are going to go more and more towards. And so we need good benchmark, and we know benchmarks impact a lot how we do the research. So call for benchmarks, don't know. And for metrics, I think, as well. So here I've listed all of the work that I've mentioned in the talk. So this is the literature. So we had LOT, token cut, deep structure methods. So you can check them out. They are very interesting works. Also a list for zero-shot semantic segmentation. References of the work that were mentioned in the talk are here as well. I didn't put the tutorial that is on YouTube about unsupervised object localization that we did at CVPR last year, but there is, if you type my name or if you type tutorial unsupervised object localization on YouTube, you will find it, if you want more details about certain methods. Or you can look at the survey as well. Obviously, none of this would have been possible without all of my co-authors. There were a lot, and it's big collaborations between different people who helped with experiments, who did, but anyway, so big collaboration, and I'm very thankful for the great works. And so in conclusion, we can't find objects without knowing anything about them. And probably that's also a direction that we want to have so that we don't have biases of annotation that have been poorly made, etc. Self-supervised features are very powerful, and they are this big machinery that we can use to and exploit, and we should, to extract whatever information we want. We can easily extract one object or localize all by looking for the background, so that's the second work. And finally, this is a bit dull comment, but we can leverage open vocabulary features to densely assign prompts to pixel. So that's it, and questions, if you have any.
Okay, thanks. So while we go for questions, I'll give the mic to the volunteer. You can spot them, and they'll go around. One very brief question. Yes. You did not mention, but your work is open source?
Yes.
Okay.
Yes, all the codes are online on GitHub, and with some demo that I think might be broken, but I have to. But all the codes are online, and you have the paper as well on archive, so they're all free to access.
With model and weights?
With model and weights. Yeah, yes.
I want to highlight that. I knew that it was open source, but I wanted to highlight that because the community is needing these things, so really reuse her work. So if you have question, just ask Loyani.
Okay, thank you very much for that wonderful presentation. I want to ask about lost, the very first part. Yeah. So is it possible for it to discover more than two objects?
To detect two objects. So the question is, can loss be used for two objects?
Yeah.
And I think it's a bit what Cutler, the paper, did. The way they did it was to detect the object, then remove them from the graph. You remove the nodes corresponding to the first object you've detected, and then you go again with the same method.
Okay.
And if there is a second object, you probably detect it that way. The thing though that I think is tricky is you don't know if there is a second object or not, right? Because you are doing unsupervised. So sometimes you might hallucinate that there is an object which is not there. But yeah, that's a good question. We actually had tried something and then we didn't continue, but yeah.
Thank you very much.
Thank you.
Okay, thank you for amazing presentation. My question is that how to handle problem of label noise on weak supervised machine learning.
So you mean the noise in the annotation of clip, or you said weak annotations?
On clip.
On clip. And what do you mean, which type of noise? Like wrong words on the maps or in the text?
Not on the text, on the map.
On the map. So that's what we try to do with the guided pooling, where you take the information from what should be connected or not from the self-supervised features. So you're trying to know which patch corresponds to one object. And that did help to remove some of the noise. Now, if you have hallucinations that are still made, then you will not solve the problem of the hallucination with this strategy. And that's a bit more tricky. We actually worked, I didn't mention it's now on archive actually, I should have put something about it, but we had a follow-up work where we tried to find negatives, because in order to remove the hallucinations, one way is to find which is something to contrast, because clip is a contrastive method, and you want something that has a higher similarity than your object to the text. And so what we observed is that you can predict, you can find text negative that you can give in the prompt along all of the other prompts, and which will help in removing the hallucination, if that makes sense.
Yeah, it makes sense. So
Yeah.
what do you think that the limitation and the challenges of this week supervised machine learning?
So I think hallucination is a big one, and that's why we had this work on negatives, and we did it, and it's great, but I think if you can push it more. So what we have done in the work is we try to find the words that are meaningful in database, or try to use an LLM to predict those words, but probably you can do something smarter. So I think maybe you want to train something to find the good negatives. Because one example I can give you, maybe that really struck us, is you have the boat and the sea. And in clip, sea and boat are very close in the space. Why? Because often they are in the same sentence. Or like you have a boat, you have a sea, and the boat is never not on the sea. So whenever clip has seen boat in the text, it also has seen the sea. But now if you put sea in the prompts, then you will be able to separate the boat from the sea. So that's what we try to work on. But so in this direction, I think there is lots of nice work to do.
Great. My last question is that, from your experience, on which problem domain do this week supervised machine learning works best?
Can you say that again, sorry?
From your experience, on which problem domain do you think that this week supervised machine learning works best?
What is a big problem? Or like what is the main problem?
I don't know. Any problem domain?
Yeah, I think what I really tried to work on was light. Like I like light things that you can train in 1 hour, etc. And probably And I think that's something where self-supervised features contain what you need, and so thinking of light ways to extract information, I think, is very nice and challenging. And there is work to separate the object, for instance. If you want a challenge, it's with those methods. If you have two dogs next to one another, because they are very close in similarity, they will always be detected together as one object. So we need something to separate the two dogs, go to the instance level, and I think that's a big challenge.
Thank you. Thank you.
Sure.
Anyone for our last question? All right. I'm remembering you that we will have the mentoring lunch, so you can also have not one-to-one, but almost one-to-one with Oriane and with the others. So let's give a hand to Oriane for her amazing talk. No, that's fine. Give it to Pierre-Roger. All right. Very relevant topic also with the audience and the topic of the workshop as well. I'll let you connect. Meanwhile, okay, I'll introduce. Now we're going to have Pierluigi Zama Ramirez. Am I saying it correctly?
Yeah, perfectly.
Hello? Okay, roughly correct. Pierluigi is assistant professor at the University of Bologna. He finished his PhD in 2021.
Yeah.
So kudos already for being an assistant professor early. Well, he's working on a number of topics, but today he's going to talk about neural processing of 3D neural fields, something also very interesting. I know a few people in the audience that are interested by that specifically. And you're working on quite a number of topics on visual perception, domain adaptation, generalization. I know you work on that one particularly, but I know that you won't talk about DA and DG today, right?
No, I won't talk about that. I will talk about neural processing of 3D neural fields. That is our latest research topic of our lab, and I think it's quite interesting as a topic. It's an emerging topic, so.
Awesome. Then
okay.
I'll let you the floor. Let's give him a round of applause.
Thank you, Raoul, for inviting me and for this opportunity. So, as I just said, today I'm going to present you this new topic that is the neural processing of 3D neural fields. So, maybe it's an emerging topic. Maybe some of you don't know some basic stuff. So, I will start slowly introducing some basic concept you need to follow the presentation, okay? So, first of all, let's start from the basics. So what is a field? Because we will talk about neural fields, so we need to know what a field is. And in simple terms, a field is a quantity that is defined for every point in a space, in a domain, okay? So let's take an example that maybe a lot of you knows from physics. The magnetic field is a field that defines for every point, for example, here in the 2D space, the magnetic force of that point, okay? We have a lot of examples of fields, like also in physics, we see the gravitational field, that's another example of fields. But the field is a useful mathematical entity that we can use to describe also real signals and objects, okay? For example, images. Images can be seen as a field. Indeed, we have a domain that is the image plane in which we have pixel coordinates. And for each pixel coordinate, we define typically an RGB intensity, so 3 values. And this can be seen as a field. So the domain is the image plane, and the field value is the RGB, field vector is the RGB intensity. There are other fields, like, for example, explicit geometry that are used to define some standard geometry, like a 3D paraboloid. You might be heard about implicit function, maybe, like this sign distance field. This is a kind of field that is typically used to define implicitly geometric entities like surfaces. Okay, so in this case, for each point, for each 3D coordinate, we have the field values, that is the distance from that 3D point to the closest surface. And is signed because it is positive if the point is outside the surface, or it's negative if the point is inside the surface. Okay? So neural fields are nothing more than a field, but parameterized by a neural network. So typically these neural networks are simple, like a multi-layer perceptron here. And this multi-layer perceptron takes as input the coordinate and gives as output the field values. So, for example, neural field for images, in this case, our MLP takes as input 2D pixel coordinate and outputs the RGB value for that pixel coordinate, okay? And so, of course, we need to optimize this MLP for each pixel in a classic training loop. And once this MLP is trained, the interesting thing is that we change the representation. So we went from an image that is defined as a grid of pixels to an image but represented as a set of weights, okay? And we can use this trained MLP or neural network in general to sample at each pixel coordinate and obtaining the color values for each pixel to reconstruct the original image, for example. Other examples of neural fields, for example, for 3D shapes or 3D objects, is the sign distance field I told you before. So in this case, we train this multi-layer perceptron to estimate the sign distance field value for each 3D coordinate in space, okay? And once this neural network is trained, we can use it to sample a lot of 3D coordinates, obtaining the corresponding 3D sign distance field values for each of these coordinates. And once we have collected a grid of SDF values, we can use further mapping techniques. For example, we can use a marching cube algorithm to extract a 3D discrete representation like a mesh from these SDF values, okay? Another example of neural field that became really popular nowadays is NeRF, neural radiance field. In this case, this MLP or this neural network takes as input 5 coordinates that are the 3D coordinate in space plus 2 coordinates for a view direction, so the rotation of the camera approximate like this. And outputs for each of these input 4 values. A density value, sigma, and a RGB free values for color, RG and B, okay? And this is called radiance field, okay? And if we integrate a long array casted from a camera, we can get the color of an image and of a pixel in an image. And this process is called volumetric rendering. That is another kind of forward mapping. So from this trained NeRF, neural radiance field, we can actually render images from any viewpoints we care. And so typically the main application for NeRF is novel view synthesis. But it's also really interesting because this is a new way to represent objects, okay? So we can represent the appearance and the geometry of an entire object with a set of weights of a neural network. So maybe some of you might ask, okay, but why? Why do we need to do that? So first of all, in nature, typically, signals are continuous. So they are defined in every moment, and they have continuous values, and they vary continuously during time, okay? But typically, when we need to process them with our digital devices, we discretize them. So let's take an audio signal, for example. So to make it to store it in our digital devices, we sample along the audio signal in some specific timestamps, and we discretize, so in time, but also we discretize the value, so the amplitude of this audio signal. And this happens also for other signals. For example, in the light beams captured by a camera are discretized to obtain images that are a grid of pixels, and for each pixel we have a color, and also the RGB color is discretized depending on the number of bits we use to represent it. Of course, also data captured by 3D sensor are discretized, and then for the 3D domain, there are also a lot of other problems because differently from images where we have a standard representation that is a grid of pixels, in the 3D domain we have several different ways to represent the same object. We can represent an object with a voxel grid, so a set of cubes that can be occupied or not, a set of points, so a point cloud, or a set of vertices and faces, so a mesh. And all these discrete representations coexist because every representation has its own advantages or disadvantages. What changes dramatically with neural fields? With neural fields, if we neuralize a signal, let's call it neuralize, so if we represent a signal with a neural network, we can actually represent the signal continuously. This is because this neural field is a function, and this function can be sampled in every possible continuous coordinate. And for each of these coordinates, we will get a value. So in this way, that means that we can estimate continuously the value of the represented signal. Of course, this represented signal is approximated, so there will be an error with respect to the original signal. But yet, we do not suffer from the discretization problem. And this leads to some really interesting properties of the neural fields. So for example, we are completely decoupled from the spatial resolution of the represented signal. So we can theoretically have a signal represented at infinite resolution with a fixed memory footprint, okay? So that are the number of ways of this MLP. And we can also, as the signal is represented continuously, we could sample, for example, the MLP at different coordinates to obtain images at different resolution. As you can see from the video here, you can see that the image represented by a neural field, we can zoom like almost theoretically infinitely into the image, preserving the good quality of the signal, okay? And of course, the fact that we have just a set of weights stored in our device instead of millions of pixels, it gives us some memory advantages, okay? So these plots here show you a nerve with 50K parameters that were enough to represent with a good level of accuracy several 3D objects. And the memory occupancy, the number of parameters of this nerve with respect to the number of points of a colored point cloud, of the number of images. And we can see that one nerve corresponds to a point cloud, for example, of 8,600 more or less points. And it corresponds to 36 images at the resolution of 22 by 22. But with our nerve, of course, we can render images at whatever resolution, at infinite resolution, at whatever viewpoint, okay? So we can gain a lot of memory space in our devices. Another really nice advantage of neural fields is that they can represent many different kind of signals, okay? You can represent images, you can represent with a neural field a video, you can represent an audio signal or a 3D shape, or the appearance and the geometry of an object with a nerve. And all these signals would be represented in a common way, in a unified way. So that is a neural network. Okay, so this would allow us to develop new processing pipelines, okay, that takes as input neural networks, that is the common representation for a multitude of signals, instead of developing a pipeline specific for each kind of signal. For all these reasons, these neural fields gain popularity. And so this is a plot of the number of applications on neural fields until 2021. And you can see already there is an exponential trend in the number of publications, showing that the number of publications are increasing in these years. So they are really a hot topic. And there are also papers that propose data sets of, for example, here I show 2 data sets of nerve. So when you go to the website and you download the data set, you download only neural networks. You don't download the images, you don't download the discrete representation we are used to, but there are only the nerve on this website. So they are becoming an independent modality that can be stored in our devices and communicated independently. There are tools a lot of tools. I just put here 3 famous tools to handle nerve and neural fields, but in general, but with these tools, it's really easy to create a new neural field, to train your neural field, or to just visualize a neural field, okay? And there are also companies like Luma AI that, understanding that the neural fields are quite have a good potential, the core business is based around this neural field topic. So maybe you now understood that these neural fields are really have a lot of potential. But before going deep into the main topic of today, I would like to just make a clarification. If some of you maybe knows about other terminology are used maybe with some errors sometimes, so I wanted to be clear. Neural radiance field, if you know it, is a lot of times, also when my paper were reviewed, they are used like synonymous. But the neural radiance field is just an instance of the neural fields, okay? Another terminology that is commonly used is implicit neural representation, so INRs. And also this was born because in the first works that were representing 3D surfaces with neural networks, and in that case, they were using implicit function like SDF. So really an implicit function represented by a neural network, and for this reason, implicit neural representation. But they are a slightly different thing from neural fields that are a more general concept. And also coordinate-based network is another way of calling neural fields that is typically used, but the coordinate-based network is just an architecture, and it's better to use the term neural field in general. So let's dive into the main topic of this presentation. So the neural processing of 3D neural fields, okay? And we'll talk about some recent presentation of my lab. And what is interesting here is that the question here is that, okay, neural fields are becoming an independent modality that is stored, sent independently, and needs to be processed independently from other modalities. So we can't if we have a nerve, an MLP, we can't always render images. That is a costly operation. We need to process nerve as they are, so as a neural network, okay? And so this was the research problem. We addressed it in our first paper on this field that is called an F2VEC. So we needed to find a way to design a neural network to process other neural networks to perform various visual tasks, like, for example, classification, generation, part segmentation, retrieval, surface completion, surface reconstruction, and whatsoever. Okay. So the first insight we had is that we started by considering only neural fields composed of an MLP. Okay, and so the first intuition we had is that MLPs are a redundant parameterization of a signal. So we do not need all the weights to really have all the information we need to perform downstream tasks. So we can compress all these weights into an embedding, a small embedding, to perform later downstream tasks like classification, generation, retrieval, etc. However, how can we design this NF2VEC encoder, as this network needs to process other networks, okay? So the naive idea would be to use another MLP. Okay, it would be to use another MLP. So take, for example, this is a neural field from a NeurIPS 2020 paper, is one of the most used. And the basic version, it has 800,000 of weight plus biases. So that means that if we need to design an encoder to process this neural field, only the first layer of this encoder would have 800,000 nodes, and the hidden dimension would have like 1,000, multiplied by the hidden dimension, if we have an hidden dimension of 1,000 neurons, the first layer of this naive MLP encoder would have 800 millions of parameters. So huge, and it would not scale well with the dimension of the input neural field. So what we did is, okay, let's use a different kind of representation, input representation. So we take, in our NF2VEC work, we take all the weights of a neural field, and we decided to stack them, forming a matrix with several rows. And then each of these rows are processed independently with a shared MLP, small MLP architecture. Okay, this MLP would be much smaller than the naive MLP encoder. And then for each row, we extract an embedding, and we can use a max pool operation to obtain a global embedding that represents that neural field. And of course, this global this way of processing, it's an approximation. We lose some information. But yet, we notice that is enough to retain all the important information needed to perform downstream tasks. And of course, is really parameter efficient, because it's independent. Our parameterization is independent of the number of layers of the input and neural field, and it scales gracefully with the number of hidden neurons in the hidden layers. Okay. So our encoder, as you can see here, has always around 3 million of parameters, independently of the size of the input neural field. So now that we defined an architecture capable of taking as input neural network, so how do we train it? So the second main question was, okay, what do we need in this global embedding? So we want this embedding to contain the same information of the input neural field, the same signal information, of course compressed, but the most important information should be retained. What we proposed is to train this encoder in a self-supervised way with an encoder-decoder. Also because, so in this way, we do not need any labels, and we also note that is extremely effective. So the training protocol should be the same of the input neural field. So we wanted to train our encoder and decoder in the same way we train the original neural fields. So if we take here for the example of how the neural field general training framework is made, we typically sample coordinates in the input domain, and we feed this coordinate into our neural network, and this neural network estimates field values, and then we use this forward mapping operation like the volumetric rendering that typically are differentiable to obtain the discrete representation where we have the data to supervise this framework, so like an RGB images. And in this way, we can train our neural field. An F2VEC is trained in a similar way, but in this case, we have an input neural field that goes through the encoder, and we extract the compact embeddings that represent globally this neural field. And this compact embedding goes into a decoder. This decoder is also, let's call it a shared neural field, because it takes as input the coordinate and the embedding and try to reconstruct, and it goes through all the passages. So estimates field values, then goes through a forward mapping, and is trained directly on the discrete representation like images. The only difference is that neural fields typically are trained on a single instance, while this decoder is trained on the whole data set. Okay? And once we train this system, we can take an unseen neural field, for example, that goes through this encoder, and we extract a compact embedding of this unseen neural field. So the first question is, okay, we trained everything with a reconstruction objective, let's call it. So what are the properties that arise from this latent space? What properties does this latent space have? So first of all is well organized, so we can interpolate between two different neural fields, obtaining a new neural field. How do we do that? So we take two neural fields as input, and we obtain two embedding representing the two neural fields. We can interpolate between them and go through a decoder, our pre-trained decoder, and in the end, thanks to a forward mapping, obtain the discrete representation. And this means that here are some examples. So given two neural fields, maybe representing, if you take the second row, two assigned distance fields, and here we visualize the meshes thanks to the marching cube algorithm. If we interpolate between these two meshes, two beds, we generate novel beds with an appearance similar to the original two. And we can do, if you see at the last row, what we can do is also to generate new nerves in this way, so that are in the middle, interpolate between nerves. So if we have a nerve of a table, a blue table, and a nerve of a wooden table, we can obtain all the tables in the middle with a similar appearance and geometry of the two. So another interesting property that came out from this pre-training was the retrieval, was the semantic rich organization of this latent space. So if we have an unseen neural field, and if we extract a global embedding from it, we can search with a simple KNN search into our database of embeddings, find the closest one, and what we notice is that the closest are all of the same class. So, but not only of the same class. This kind of of training objective allowed us to retain a lot of appearance information and geometric information of the object. So if you can see, if we query with a nerf of a red sportive car, the closest instance retrieved are old red cars with a sportive look like. And if we go farther, for example, the 100 nearest neighbor is still a car, so it's really well organized. And of course, farthest objects are different, like chairs or other classes. Another thing we tried is to train a linear classifier on the top of this pre-trained NF2VEC encoder. And so we try to classify what object is represented inside the neural field, so inside the neural network. And what we noticed is that this kind of architecture was obtaining results comparable to those that were using discrete representation like images, point cloud, or meshes. So with the difference that we have for classifying images, we had to use a ResNet. To classify point cloud, we had to use a PointNet or something similar. To classify a mesh, we used another architecture, and so on. While to classify Hello? Okay, sorry. And to classify a neural field, we can use the same architecture for all these kind of, instead of what we do typically with discrete representation. And another real benefit is that it's extremely fast. So in this scenario in which neural fields are an independent modality, that is, maybe you can download a nerf of an object, for example. If you want to use a traditional pipeline like a ResNet to classify the image, you need to render those images from the nerf. But processing directly the weights is extremely fast. For example, it takes, on the right you can see it takes 1 millisecond to classify a nerf. While if you have to render and then classify, it takes 10 or 100 times more. Another question we make is, okay, there are enough information in this compact embedding to classify objects. But what if we want to do some more fine-grained task, like segmenting in 3D the represented object? And what we notice is that also in this case, if we train a decoder on top of the pre-trained encoder, also here, we can see that all the objects are well represented, are well segmented. And you can notice here is the task of part segmentation. So given an object, we need to segment its parts. And we could do that only by processing the weights of the neural fields. We also tried another task that is generation. So we wanted to generate new neural fields. And what we did is to train a simple latent GAN, so a generative model trained on the latent space directly and on the embedding space of an F2VEC. And then using this generator, we can generate novel embeddings in the training distribution. And these embeddings can be decoded to obtain new fields. And as you can see here, these are examples of discrete representation extracted from generated neural fields from our system. In the bottom, you can see that the generated neural fields, like a new nerve, is still 3D consistent. So that's interesting because you generate a novel nerve, a novel embedding, and if you go into the decoder, you can render this new object from any viewpoints, okay? We also explored some interesting ideas. So what if we learn a small neural network, a mapping network between the embedding space full, for example, from the car where almost all the car is missing to the space of complete cars. And we could do, and in this way, learning this mapping allowed us to perform the shape completion task. So when we get an unseen neural field of a shape that is incomplete, we can generate automatically the complete shape. We can do more. We can learn a mapping to map a neural field that represents only a geometric signal, like a point cloud, to the embedding space of neural fields that represents both the geometry and the appearance, like nerve. And in this way, we can hallucinate the nerve of an object given only geometric information of it. We can also use it to reconstruct a mesh given point clouds. If we have, in this way, we go from assigned distance field to the signed distance field embedding space. Okay. So now we have seen that this compact embedding retain a lot of information that can be used for visual tasks. But are the information contained in this embedding enough to perform language tasks? So to understand maybe a nerve, so a neural network that represents an object with an LLM, for example. So that was the idea that led us to explore this new framework that is called LANA, that is a large language and nerve assistant. And in this work that is still under submission, we take the NF2VEC encoder pre-trained, okay, and we take a projector layer and a pre-trained LLM like Llama 2, and we try to fine-tune in a similar way. We took inspiration from Lava, so instruction-based. And what we did, what we found out is that it's possible to actually chat with a nerve, to actually take the weights of a nerve and understand a lot of details of and chat what is this nerve representing, what is the color of the object, and other kind of question. And to train this LANA, we had to collect a data set, but of course, collecting manual annotation is extremely expensive, so what we did is to create an automatic pipeline to generate a data set, a training data set. So it's based on synthetic object for now. So we have a synthetic object, and we can render multiple images of it. And using a pre-trained foundation model, multi-model foundation model like Lava that can process images, we obtain a caption for each of the rendered images. And this generated caption can be aggregated using a LLM, a pre-trained LLM, like we used Llama 3 for this. And we obtain a multi-view caption that should retain the information of the object, holistic information of the object from every viewpoint, okay? And then we ask to the same LLM, to Llama, to generate ground truth to train our system. So we generated ground truth for brief descriptions, detailed description, and question answering on nerves. And these are pre-training our system, training our system on this dataset led us to this kind of result. So you have to imagine that the input of this system is a neural network, are weights of a neural network. And we could ask, okay, describe the object, but describe the object that is represented into this set of weights. And the model can answer that is a boat with blue and red colors, and it gives you a lot of details of the object represented inside the nerve. And also we can perform clearly Q&A, so we can chat about what is the color the primary color of the boat, what is the shape of the boat bow. So to answer this kind of question, the model needs to have an holistic understanding of the object, because some questions are really made, are possible to answer only if you see the object from a particular viewpoint. So that's interesting that if we process the weights, all this information, the holistic information of the object is retained if we process this directly the weights. And here are other examples of nerve that we were able to process. These are the video you see, or the objects you see, are renderings obtained from a pre-trained nerve. So, okay. So this is it's just for visualization purposes. You have to imagine that the network takes weights. We also compared, of course, with other. You can't read it, I think, but you can. We compared with other multimodal LLMs like Lava or Point LLM that operates on images or on point clouds. And what was interesting is that our method performed better on this kind in our task, in our data set. So to conclude, I want to highlight that this neural processing of neural networks, and in particular of neural field, is an emerging topic. So maybe a lot of you didn't know about this possibility, but it's a field that has a lot of space for ideas, a lot of space for innovation, okay? And the first work on this topic was at ICML 2022, followed by our work. And in the last 2 years, 1 year and a half, we had several papers. I put here some of the most important. And so, I don't know, is it possible to read the, no. So, maybe I can zoom in. Anyway, yeah, there are a lot of papers. If you are curious, you can ask me or send me an email or whatever. They can send you some references, okay? And so, as I was saying before, this is there are a lot of open problems and interesting research direction. So first, an example of open problem is that all the meta encoders we designed can process a specific neural network, for example, an MLP. But typically, we have a lot of different architecture. We can have transformers, we can have convolutional neural networks, we can have hybrid architecture with maybe a feature, some set of discrete feature plus a neural network. And we would like, in theory, to have an encoder capable of processing all the types of architectures. The other problem is that for now, everything is tested in synthetic setups. Or in the case, there are works that do neural fields, that process neural field of images, and they are trained on Cypher-10 or really, let's call them toy dataset, but not toy, but still they are not ready for being in the wild, let's say. And another key problem here is the random initialization of neural networks. The neural networks, as you know, typically are initialized randomly, and this leads to, during the training protocol, during the training phase, to obtain networks with also with the same task, the same data set, train the same task on the same data set. If they start from a different initialization, they could converge to a really far point in the weight space. This leads to problem in the generalization of this kind of architecture. So there are works that try to address the random initialization problem, but it's still the beginning. So there's still a lot to do. And also in the case of 3D object as my presentation, it would be interesting to extend these works to scenes. So not just objects, not just single object, but also having, for example, a nerve of an entire scene and being able to question with an LLM, with natural language, question your nerve. For example, given a nerve of a room, how do we find the yellow mat? Or maybe I can ask, how can I go from the kitchen to the toilet? All these scene-related tasks would be an interesting direction, and there's almost nothing on this. And another interesting direction that maybe is also out of solely computer vision would be to extend these works on neural processing on neural fields across signals. So as I said at the beginning, the neural fields are capable of representing various kind of signals, audio, video, and images, and whatever, not just 3D objects. And it would be nice to have a unified architecture, a multimodal architecture that operates on every kind of signals, and this is extremely general. Okay. So here I thank you for your attention. Here you can find some QR code that links to the project pages of the work I presented, plus another work we recently published that I cleared, that there was not enough time to present. And but if you're curious to know more, you can take a picture and go to the project pages. So thank you.
Thanks a lot, Pierluigi. I know there are questions. I'll give the mic to the volunteers.
Thanks for your great presentation. So I find this quite interesting, and I have a couple of questions. So the first one is, you mentioned when you are running inference from your nerve to get probably classification or whatever your final output is, that you can get fast inference, but like slow rendering is the challenge there. But I may have missed it. I did not hear you talk about how much time it takes to actually go from the original signal to the nerve. Is that slow? Is that fast? How much time does it take?
Okay, so training a nerve can be time consuming for sure. But the idea here is that nerves are becoming a popular independent modality. So there are data sets online that already where you can download only the nerve, okay? So in that scenario, it would be useful to process the nerve in a fast way. But of course, we are imagining a scenario where the nerves are already available, where you don't need to train it. If you want to train a nerve, there are pipelines that can be really fast nowadays. There were a lot of works that try to address this problem. And for example, the nerve on an object, we try to use an extremely, when training a nerve of objects in our works, we used an extremely efficient pipeline, and it needed like 15 seconds to train on a standard GPU like a 3090 NVIDIA. So.
Okay, I think that makes sense. So it's possible, even if it takes time, to do that like as an offline process and use the nerve online. Yeah.
The thinking is, the forward thinking, let's say, is that they will be available already. Okay, you don't need to take the images, train the nerve, and then use our pipeline. You take the nerve and they use our pipeline. So that's the idea.
Okay, yeah, thank you. My second question is probably something to do with the slides. I'm not sure if you can go there. But on the learner slide, you talked about something called a projector. I'm not sure if you can go into more detail about what a projector is.
Just a bunch of layers. I don't remember the exact implementation details. It goes from, it's needed to map the latent space of an F2VEC into the language aware space of the LLM. So it's quite small. I don't remember exactly I need to check the implementation details for that.
Thank you. Are your slides
It's
available
quite small,
publicly?
it's tiny.
Yeah. Final question is: do you have are the slides publicly available, or I can access them somewhere?
What, sorry?
The slides, are they publicly available, or it's?
The slide? What, sorry?
Maybe I can reply. The workshop is recorded and we will put it online. So
Okay.
yes.
I haven't noticed.
Thank you.
Okay. Yeah, sure.
Hi, thank you for the amazing presentation. So my work is in gaming, especially in virtual reality. So I'm trying to understand the application of your work in creating new environments in simulations. And my question would be, can we use your work in creating new environments in simulations?
Okay, that's a nice question. So, yeah, these kind of works are needed when, if you're using already some kind of neural networks in your engine, maybe.
Mm-hmm.
Of course, neural fields are becoming extremely popular in graphic in general. And I heard about graphic pipelines that are implemented with leveraging a lot neural fields. In that case, if you have a graphic pipelines with neural fields included, my work could be really useful in that case, and you could use these meta networks to process neural fields for whatever you want, or maybe have a chat interface with components. I don't know. But yeah.
Okay, an additional question. With the way you are processing the neurons, is it possible to consider using gaming engines that access the 3D space, like in virtual reality, to add more data to your neurons?
I didn't get what I should use.
Okay, so specifically in game engines, there are tools that
Okay.
can recognize objects or spaces. For instance, using the Meta SDK that actually analyzes depth of the actual space
Okay.
here and identifies the object. So those kind of tools have given a consideration on using them.
Okay, and I didn't try to use these kind of tools. However, I think they could be extremely useful in the case you would like to scale up everything to scenes. And in that case, maybe recognizing the object in the scene would be really interesting with these tools. But yeah.
Okay, maybe just a quick question. You mentioned that so far neural fields are trained on toy dataset.
Mm-hmm.
Why and what are the challenges for it to be trained on real-world dataset?
So actually we are already moving in this direction in our team to generate nerves for real objects. And there are also already available several data sets that provide nerves for scenes and pre-trained, so you don't need to do anything. And in that case, and of course, if you want to stick on objects, you could simply train our system in nerves on real object and understand how well it performs. If you need to go into scenes, maybe you should change something in the architecture also. So
okay,
it would
thank you.
need some work.
Yeah, sure. And maybe what are the potential application domains of the neural fields?
So I think the potential are enormous. So first of all, my address a scenario in which neural fields are everywhere, In that case, of course, you could perform all the tasks we are used to perform directly on the weight of the neural network, but also it could be useful to, as I said before, to have a single way to process several different signals. So audio, point clouds, images, instead of putting a lot of efforts in developing several different architecture, you can build a single architecture that can process everything. Also, that would be a nice application. Okay.
Very quick. How did you evaluate the quality of the description generated by the LLM at the end?
Yeah, we had a lot. So for training, you mean? Because for testing, we used a human created data set. So during training, when generating the training data set, actually we had to to understand we simply look at the statistic of the data set and how the question looked like. We also did an experiment like how well these kind of questions are correlated. So if there are correlation between the questions and the answers. So we pre-trained a model without the neural field in input, so just with text, so just on question, and we look at its performance. And so to look at the correlation between question and answers, we visualize like keywords in the data set, and let me think if we did something else, because we did a lot, especially for the rebuttal period. So yeah, but mostly statistics and experiments in which we try to use LLMs to analyze the data set itself. So other LLMs to analyze the data set. So yeah, it's not manually curated.
Okay, I'll stop the question, but you'll have time to discuss with both of the speakers that you've already seen during the coffee break. Let's give a hand again to Pierluigi.
Thank you.
The coffee break, I'm just gonna put back the screen. So this is coffee break. Just if you can put the computer again, computer screen, please. During the coffee break, yeah. Just I'm putting back again the mentorship QR code. You have the URL below if you cannot scan. So this is for registering to the mentorship lunch, which is having a small group interaction with our speakers. And we'll resuming the workshop at 11:15. Have a good coffee break. See you around. La régie, est-ce qu'on peut laisser l'écran pendant le coffee break? Voilà. Pendant toute la pause, s'il vous plaît. Merci. Okay. All right. All right. While we look for the last speaker that is around in the conference, the last speaker of the morning that we cannot spot, she's around, Candace. If someone knows where she is or has her phone number, don't hesitate to send a text. But while we do that, we're going to resume the workshop. Just a word to say that I've seen that a number of you has registered to the mentorship lunch. It's officially crowded, so I think the people that were late is going to be a miss for you, because we don't want 10 students around one speaker eating and having 10 questions at the same time. Okay, and we're going to resume the workshop in the morning. We're going to have two shorter presentations, one from Daniel Adjisafe and one from Candace Ross. And introducing Daniel, we're really happy to have you on stage with us at the workshop. Daniel is currently a PhD student at the University of British Columbia. He's being supervised by Helge Rodin and Andrea Tagliacci. I never know how to say his name. And I think you're from Nigeria originally, yes? So he was there also with us yesterday. But maybe the most important highlight to give about Daniel is that Daniel, I know him a bit, and he has been, in fact, volunteer at the workshop in 2022. And most importantly, the winner of the Best Paper Award last year at the workshop. I'm always saying, if you volunteer 1 year, be ready to have the award the next year. Daniel, we're really happy to have you here. Happy to see your work, and just mentioning that Bastien and Helge, that I see on your supervisor, as part of your supervisor, are also involved in the African Computer Vision Summer School that I told you about this morning. This is this shirt. Daniel, the floor is yours. Welcome and have a good presentation.
Thank you so much. Thank you so much. I'm very grateful for that wonderful presentation. I'm honored. All right, my name is Daniel Adjisafe. I would be focusing on learning human body pose, shape, and appearance from mirror videos. We also call this mirror-aware neurohumans. I would say some of you might actually be familiar a bit with this work, but not everyone actually knows what's going on behind the scenes. And the talk basically is to really uncover what's going behind the scenes. This is also a work that has been published at the 3D Vision conference this year as well. So I look forward to work on this journey together with everyone in the room today. All right. So we humans, we move, we navigate, we are essential parts of this world. And it's very important for us to develop algorithms that can reconstruct us ourselves in full 3D digital form. But to develop such kind of algorithms, we need enormous 3D data to be able to achieve this task. So prior works have tried to use marker suits to collect this 3D data as ground truth, but this can be very expensive. Other efforts have tried to purchase multiple cameras and then triangulate them together to give you the same objective, but this requires that these cameras be temporarily synchronized, and they can be quite expensive as well. But in contrast, we have mirrors. And mirrors are affordable and available alternative. They are quite common in urban areas. And also, mirror provides extra information, which is in the form of our reflections that we can see in the mirror. All right. As at the time of writing, there were two leading prior efforts in this area. One of them is Fang et al. And Liu et al. Fang et al. Made us understand that human poses can almost look very perfect in 2D, but when you go into 3D, the ambiguity of these poses is quite revealed. For them, they proposed mirror-based optimization approach that could resolve this ambiguity in 3D. But the challenge is their method requires manual annotation, which can be quite laborious. The other method, Liu et al., proposed a method that resolves occluded joints, but their method is quite limited to just reconstructing 3D locations and do not take account of joint orientations, which means that this can lead to incorrect pose sequences. In any case, both methods actually also do not take into account a detailed reconstruction of the person's shape and appearance, which is quite important, and we'll see why later on. All right, so what do we do differently and how do we do things differently? So we can understand that the image of a real person, say for example in this 2D image, can actually be produced by a real camera in a 3D space, as well as the image of the virtual person in a mirror can also be produced by the virtual camera, as we see as well in the 3D space. While we as humans, we can see where the mirror is in the 2D image, the question is, where exactly is the mirror position in the 3D space? To answer this, I usually love to use this example, which was something I discovered even after the project. In a real life scenario, if you stand in front of a mirror and you go close to the mirror, you realize that your reflection will come close. And if you go farther away from the mirror, your reflection goes farther away. This simple intuition analyzes that the mirror position is just a symmetric interpolation of the direction that goes from the real person to the virtual person. And this way, we can automatically estimate the mirror position without manually annotating the mirror. Building on that intuition, we can also use the direction that goes from the real person to the virtual person to also calculate the mirror orientation as well automatically. Subsequently and furthermore, with the mirror position now calculated and the mirror orientation now solved or resolved or known, we can also use this to now calculate and estimate both the position and orientation of the virtual camera that stands behind the mirror. All right. Other things are also important for us to address as well. I don't know if you've noticed, if you stand in front of a mirror and you raise your right hand, it will appear as a left hand. I don't know if everyone have noticed that. But this is a big challenge for an algorithm to detect. The question then is, we as humans, we know who is real, we know who is the virtual person. But how can we make an algorithm deterministically and automatically know who is real and who is virtual, and do it in a more principled way? We live on the understanding that the indirect light that goes from a camera to the virtual person in space is usually longer than the one that goes from the camera to the real person. This, in essence, means that the real person is actually closer to the camera, while the virtual person is further away in space, or to the space. So as a result of that, we develop an automatic mirror person assignment that uses a pelvis to neck bone distance, where the pelvis to neck bone distance will be longer for the real person and will be shorter for the virtual person. And with this, we can automatically do this association. All right. Now, having resolved these missing but important details in the geometry, we are able to then move on, because these missing details are all in step 1. So having resolved all of those missing details in step 1, we can then move on to step 2. Now, what is step 2? Step 2 basically is very simple. It's a classical multi-view optimization, 3D optimization, that tries to minimize the reconstruction error given the real pose and the virtual pose. Also, we also leverage extra things like additional smoothness and also fit constraints to make the reconstruction even much more accurate and plausible. All right. Now, moving away from step 2, we move on to step 3, which is quite interesting. Step 3 is what we call neural rendering, because this neural rendering is, as previous speakers also mentioned earlier as well, you mentioned neural radiance fields. So this is also a variant of that, where you want to have detailed appearance, and you want to see things in a more photorealistic way. So we leverage existing articulated neural radiance fields, NF and DAMBO. Our representation is very simple. We use static bone lengths, joint rotations, bone vectors, positions, things we've already optimized and solved for in earlier steps. And we also use an affine transformation, which essentially is just saying I want to go from a local space to a word space, and I can also go from a word space back to a local space. In terms of rendering, we use basically input images from a video. Video gives us those information, and we will use the joint orientations that we've optimized for in step 2. And neural rendering essentially is just, ray casting, pixel locations from the mask, and the masks are all detected, which goes from pixels to the 3D space. And we can then sample points along this ray direction. The goal would be to feed these sample points, these queried points, into an MLP. And neural radiance fields, which is abbreviated as NERF, is simply an MLP that takes in the query points and predicts color and density. With this predicted color and density, we can then train the neural radiance fields with a photometric loss and then do our image-based reconstruction. We do this on foreground mask that just helps us focus on the humans in the scene. All right. So to tie this together and put everything into a holistic view, the overview would be seen as we start from a mirror image with an unknown mirror geometry with 2D detections. We reconstruct the mirror plane, the ground plane, and the 3D key points in step 1 and step 2. Now, our optimization yields bone orientation that is very crucial for integrating NEF, which is neural radiance fields. And so the optimization helps us to generate and yield bone orientation, which is crucial for integrating NEF with mirror-based reconstruction. So in step 3, we introduce mirror-aware articulated NERF while resolving mirror occlusions. We also design a mirror image layer and a image layer such that we introduce mirror awareness into the neural radiance fields as well. So while resolving mirror occlusions, we design a layered composition as well, which is a composite image. The final end result then can be a refined skeleton, a rendered image at novel views or seen at different viewpoints, and also we can also have a 3D geometry just from videos. All right, let's go into results. So we also can see that with mirror-aware neural humans, we can align the skeletons well to the images. Essentially, it means that whatever reconstruction error that exists in step 2, for example, can be further corrected and reduced in step 3. And this is simply because at step 3, when you do neural radiance fields, the image reconstruction provides pixel-level data that you can use to even further correct whatever errors that lie or remain in earlier steps. And we perform these qualitative results on diverse sequences with beards, with shorts. We do this on YouTube videos. We try this as well on a standard benchmark, which is mirror human eval data set as well for the final model. All right, so talking about quantitative results as well. First of all, when we compare to learning-based approaches, we can see that mirror-aware neural humans actually outperform learning-based approaches that do not leverage mirror data, which shows the benefit of leveraging that extra information that is just lying there in the mirror. And also, mirror-aware neural humans as well, when compared to other approaches that actually leverage mirror-based, we realize that mirror-aware neural humans is the most automatic. Other efforts usually go on the manual route, which can be very, very tasking, but we try to make all of these unsupervised, automatic, and only rely as well on detections. All right. So mirror-aware neural humans pretty much just start from mirror images and 2D detections, and 2D detections is very simple to acquire. Our algorithm enables novel view synthesis from just these two information, mirror images and 2D detections. And we can see that given this information, you can always query different viewpoints and see things from diverse angles. So the setting is very simple. It's fixed poses, but you can also try to see unseen camera trajectories which you don't have information earlier off. Also, starting from mirror images and detections, you can go beyond novel views. You can also use mirror images and detections as well to enable learning body geometry. And with body geometry, it helps you to do a lot of things that could, say, for example, require animation and all of that stuff. So this gives you that pipeline as well and enables you to learn body geometry from just mirror images and detections. All right. So the other application that we also see for this work as well is quite intriguing. So say, for example, given a learned source body model and a new mirror setting where this learned source body model was never trained on at all, mirror-aware neural image gives us the capability to be able to synthesize novel view synthesis in a new mirror arrangement, such that, and it does it in a way that is mirror correct, such that the reflection applies in a way that everything looks as though the reconstructed body was in the scene, whereas it was never in the scene. And that really, was quite interesting for me to see this as well. And please you could see more results as well from the QR code that is placed up there as well. So, we try to come towards the end as well. So what are the potential applications of this idea and this project as well? So I find it very, very interesting to even realize that mirrors are actually used in, mirror therapy, for example. Say someone whose leg has been amputated and they are going through, a mental and physical struggle to really come back to stuff. So mirrors are actually used to help them relieve their experience and help them in their quick recovery. And this suggests potential use cases of, say, for example, a mirror-based post-estimation for leg rehabilitation. Also, the idea of reflection is not just limited to planar surfaces like mirrors. It can also be extended to non-planar surfaces like water. For example, if you just stand in front of the water, you see your reflection. Or you stand in front of a car, you see your reflection. Or even if you wear glasses that is reflective and you stay in front of that person, you see your reflection. These are subtle ways that reflection provides extra information that can also be benefited from and also taken advantage of as well. All right, bringing us to our final slides. This is quite recent. Some of us are quite familiar with state-of-the-art text-to-image generation models like Stable Diffusion, etc. It interests me that given a prompt, this is something I tried. ChatGPT actually suggested that prompt. So given a prompt, you can actually generate images that provides even more information. For example, we can see shadows, we can see reflections on the ground. It provides even 3 new information that can be leveraged as well. However, that said, limitations still exist. There's still room for contribution. For example, in the first image at the beach, we can see that the body parts are wrongly associated. The right hand is stretched forward. In the mirror, the hand should also be stretched forward, but it's backward. Also, we can also see that the virtual body shapes is not well aligned. The real person is quite shorter than the reflection we see in the mirror. Lastly, as well, we can also see that, as we talked about symmetric interpolation, that the distance that goes from the person to the mirror in this example is not symmetric. It's not the same as the distance that goes from the mirror to the virtual person as well. This just shows that there's a lot of limitations and ambiguities in current approaches, and it's exciting that perhaps introducing mirror-based alignments can even improve current generative models, because as they are right now, they don't have that sense of reasoning about what is mirror correct or what is not mirror correct. I think this brings me to the end of my presentation. Thank you.
Thanks for the, was it for you? Oh, sorry. Thanks for the very nice talk. I had a question. I was wondering, so you said you try to find which is the virtual and which is the real. And I was wondering, how much does it matter? Why does it matter to find which is real? Like, isn't it symmetrical? Or?
Yes, I think to make that very practically answerable, I'll just go to one of the hidden slides. Okay, let me show this. I don't know if it would. Okay, good. This is a very good way to answer that. Now, if you confuse the real person with the virtual person, because it's a classical multi-view optimization, you need to know who is real and who is virtual. Because you have pseudo-ground truth. So, for example, we use detectors to get pseudo-ground truth, and you need to do a reprojection. So, when your algorithm predicts real pose estimate and produces virtual estimate, you need to know which one to align and compute errors with. This is why it's important to know which one is real, which is virtual.
Because the model you're using makes a distinction.
Yes.
Okay, thanks.
And it has to be automatic as well.
All right, thank you very much for the presentation. Yeah, you were trying to relate the reflection to what we actually see when we look at the mirror, the fact that it gets to like, when we raise our right hand or we get to see the left hand. So how were you able to manage that, trying to differentiate the virtual image to the real image?
Yes. So I think the problem is actually two, and I think this would probably also apply as well. So first thing first is to distinguish automatically which is real, which is virtual, is to first leverage the understanding that the virtual person is usually farther away. So as a result of that, if you compute, say for example, bone length from pelvis to neck, for the real person to be longer, for the virtual person to be shorter. Now coming to the question of when you raise right hand, it appears as left. For that one, one thing which you can use to break symmetry is if you understand the middle part. The middle part breaks symmetry between what is right and what is left. So in such instances, we consider the real person to be more accurate. We use the real person as a reference for the virtual person. So what it means is, for example, if we start from the two detections. The off-the-shelf two detector would predict, say for example, all the key points in the body, and it tell you this is the right joint, this is the left joint. Those are pseudo annotations for you. So for example, it gives you the key point and it tells you it's the right key point. It gives you the left key point, it's the left key point. And you have that for the real person. But for the virtual person, the detector will be confused because the detector works based on what it can see. But we know that the information for the real person is right, and we use that as a reference for correcting the left. So one practical example would be that, if I share now, it will make more sense. Let's see if that comes up. All right. From this, you see that the real person, if the real person backs the camera, logically the virtual person should face the camera. That's already one intuition. If the real person faces the camera, the virtual person will do what? Back the camera. That's also another intuition. This is subtle ways in which you can break that cues.
Thanks for the presentation. You mentioned something about doing neural rendering. So I'm curious why. What purpose does the neural rendering serve in the pipeline?
All right, good. Thank you so much. I'm not sure if, I think there's a slide that was actually missed, but let me just go to the main overview. So first thing first, you can see the neural engine as primarily an icing on the cake. So the step 2 stops at that bone orientation where it's just skeleton. But with the neural engine, you won't just have skeleton, you want to have a photorealistic 3D reconstruction, something that looks real, something that you can render from different views, something that you can even put into a game engine if you want, something that can give you an avatar of yourself if you want, something that is more practical, So that's the icing on the cake. But beyond that, quantitatively, can it help you improve your results beyond just, the application side of things? Is that neural engine is an image-based algorithm. So with the fact that you use images to do reconstruction, you can leverage that pixel level photometric loss to do further improvement. So which means if there's any, for example, the first image, if there's any errors that you have in the skeleton in the step 2, by the time you get to step 3, you can use that image-based reconstructor to further refine that skeleton and you get better results.
Okay, thank you very much.
Just a quick question. Thanks a lot for your presentation. It's interesting to see a full presentation of that work that we already discussed together. How do you see that architecture being extended to semi-transparent reflection? And you're currently using the information of where the mirror plane is, right? And that information might not be easily accessible if you're talking about semi-transparent or if you're talking about non-planar. How do you see that extension in practice?
Yes, I think that's, okay, I'll just go to, yes. So actually this is, interesting because we want to really extend this to, very cases where you don't want to assume that the mirror is in a particular fixed location, and this would be water. I think the easiest place to start will be to leverage an outsourced detector first. An outsourced detector that first tells you where the virtual person is. So once you know where the real person is and the virtual person is, those provide subtle ground to be able to know where the entire reflection system would be. So for example, if the reflection person is downward, you can expect the reflection to be upward, right? So you just have to start with what is available and use those available information to now, find what you need as it is. It will not be straightforward, but I think the subtle information will be one way to start.
Okay, so going towards matching of features, right?
Yeah, so in this case, first of all, you can start with a detector. A detector that tells you the real person and the virtual person. That gives you location in 2D space, right? And from there, you can then probably say, for example, do things like understanding like triangulation, or if I were to put it this way, you can try to first understand where the reflection will be. That would necessarily be in the virtual space. It can't be in the real space. That would be a good place to start from. Maybe there might be also advanced way to also get better understanding of where it could be, but I guess it would be worth thinking about. But for now, this is what I think.
Awesome. So thanks a lot, Daniel. Let's give him a round of applause again.
Thank you.
All right. Candace, you can go and maybe plug your computer. We're moving now to the last speaker of the morning session. We are lucky to have Candace Ross today with us. You should have HDMI or USB-C. Actually, this is interesting because when building the workshop, do you need a, there is a plug there. I'm not sure that one is plugged. So it's actually interesting because when preparing the workshop, and since I was also part of the Indaba organization team, I actually spotted the name of Candace on the people coming to Indaba, and I was like, how is that possible that she's not a speaker to the workshop? It's not possible. So I think I bombed her with a number of emails saying you have to be a speaker also. Give a short talk, but come and say something here. And so it's actually the first time that we meet, but I can say that Candace is currently a research scientist at Meta. I've seen that you worked at Meta for now quite a number of years, 5 years something. And she's been before a student at MIT and in other university before. So we're really happy to have you here. Thanks a lot for being there on site and giving that talk. Let's give a round of applause, please.
Well, thank you for that really kind intro. Appreciate that. Yeah, so my name's Candace. I'm a research scientist based in New York, and I work on the Society and Responsible AI team. And so what I'll focus on today is the evaluation side for these vision language models. So So I'd say most of us would probably agree that text-image models today are very impressive. So these are just 3 different models. So on the left, we see the caption, "A dog catching a frisbee in the jungle." This was generated by Stable Diffusion XL. And it's a pretty good image. Dogs are not usually in jungles, and the model can still do it really well. Then next, this is from Dolly. We have an astronaut riding a horse in space. Again, horses aren't usually in space. Astronauts do not typically ride them, but that image looks really good. You can even specify a style. And then lastly, this is a model from Meta. A small cactus wearing a straw hat and neon sunglasses in the Sahara Desert. That text is long, it's complex. These things are not usually put together, and the model also does a really great job. So it's exciting. Our model's doing great. But I want to note that there are also some issues. These models can be a little bit funky. So if you have this text here, "A bat is flying over a stadium," the model gets a little bit confused. It's like, should I put the animal bat or should I put the baseball bat? And so it just kind of guesses and puts both. Probably not what we want to see here. They also, unfortunately, learn some pretty harmful biases. I think this has been talked about a lot at this conference. For instance, this is from one of our papers where we were generating really common objects. These were things like cars, dogs, stoves, and so forth. And we specified the regions on the left. These are cars and stoves for Africa, and then on the right for Europe. I'm imagining we would all agree that these generations look quite different. The model has a very different view of Africa than a lot of us may. And then sometimes what they generate is just completely wrong. So these 2 captions are super similar. On the left, it's a cat sitting on a dog, and on the right, it's a dog sitting on a cat. And the one on the left is great. It's correct. The cat is on top of the dog, but on the right, it's wrong. And what's interesting here is I tried a bunch of times to get an image of a dog actually on top of a cat. I added all these little captions. I added things like photorealistic style, cartoon, and the model really struggles because we don't typically see dogs on top of cats. It's a linguistic bias these models have. So even though they're really exciting and make great images, we're definitely not perfect yet. And so the examples I showed were all for generative models, but I wanted to take a brief step back, because in this talk I'll focus on 2 types. And so on the left we have our discriminative models. These are our classifiers. These are cases where we give them images or text, and we get generally text back. So for instance, we might have that image up top, and the classifier we may say, is this a cow being milked? Super confident, gives us a nice high score. Is this a cow in a pasture? Less confident, lower score. These are our classifiers. And then on the right, our generative models that we've typically seen, we might give a piece of text, a photo of a cow staring at the camera with a spotted nose, and ideally we get a really nice image out. So we have our classifiers and our generators. And with this in mind, I want to focus on 2 specific questions. So first, what makes a good benchmark for vision language models? And second, what makes a good metric for these models? And so first, we'll start with the benchmark. So I want to start with an example, open to the audience. We have this image here, and I want to know which caption best describes the image. Would you say A, some plants surrounding a light bulb, or B, a light bulb surrounding some plants? And feel free to shout an answer out, A or B. All right, hearing a bit of both. Yeah, I would say A. I think I heard mostly A's. And we'll do one more example. Similar text, just a different image. Would we say some plants surrounding a light bulb or a light bulb surrounding some plants? I hear B. Other thoughts? B's. I'm hearing B's. Okay. I agree. Let's say B. And what's fun here is that this task in general is pretty simple for humans. We won't always agree completely. I think that's true for computer vision, NLP, whatever modality you're in. But usually you can get pretty high agreement from humans. And this task is really, really challenging for vision language models, which is surprising because it seems like a fairly simple task. 2 images, 2 captions, pick one. And so to formalize this is a benchmark that we developed that we call Winter Ground. And the idea for a good benchmark is you want a task that's relatively easy for humans with relatively high agreement, but a model should not be able to hack it or just guess it. And so the way we formalize this is we have 2 images and 2 captions, and we ask the models to match the image to the caption, like we just did. But the really key part here is that the captions have identical words in just a different order. So we want this to be really hard for the model. It should have to really read that text to get it correct. And so to evaluate the performance, we have these two images, I0, I1, these two captions, C0, C1, and we have 3 scores. The first one is the text score. What we're saying is, given an image, which caption scores higher? So it's almost like image captioning, which text is better? And it gets us right if and only if it is correct for both scenarios. So for both images, you have to know which caption is correct. Then we have our image score. It's a bit similar, but kind of flipped. Now we're saying for a given caption, does the correct image score higher? So this is like image retrieval. You can think about Google image search. I give you some text, find the right images. And again, it's correct if and only if both scenarios are right. And then lastly, we have a group score that just combines the two. And what I like about this a lot is it makes sure the model can't just guess. You need to get both scenarios right. So you can't rely on those little linguistic biases. You really need to know both. So I want to dig deeper into why this setup, I think, is really important for our benchmark and benchmarks in general. So models are really good guessers, right? They see a ton of data, and oftentimes they're going to just default to what sounds the most likely. So if we have this text, so on the left, a parent taller than a young child, and on the right, a young child taller than a parent, which one do we think is more likely just to happen in the world? A child being taller or a parent being taller? I would say generally, most likely it's probably that the child is taller. That the parent is taller. Unless maybe the kid is on stilts or like a ladder, but usually young children tend to be shorter than parents. And this is what models do. Models say, I usually see parents being taller. I'm going to just go ahead and guess the parent is taller. So in our case, when we have the same words in a different order, we break that where models cannot just guess to get a good answer. So first, I'll dive into the results, but here's the human performance. See, it's 88% generally. So humans don't always agree. And we saw that even today with us. We didn't always agree, but they generally have pretty high similarity. And then random chance for those 3 scores I mentioned, 25% for text and image, 16 for group. So if the model is just guessing, their numbers will be similar to this. And so we tested a whole bunch of models. The names aren't important, but I think the key part here is that you can see models basically are getting chance performance. They don't have great visual-linguistic reasoning skills. They're not great at these complex sentences. They're basically just guessing. And it's a tough one because, like we saw, humans do a really good job, and models really struggle. So in spite of what we've seen, which is really exciting, and I think we're in a great place, models, it's tough reasoning for them. And so now we can dig a bit deeper into our data set. We labeled every example. So now let's try to look at a deeper level. We have these 3 different linguistic labels. On the left are what we call the object swaps. So for instance, there is a mug and some grass. There is some grass in a mug. This is where we swap nouns generally. We have that relation, a person sits and a dog stands versus a person stands and a dog sits. These are adjective swaps or verb swaps. And then lastly, both. And I love this example. My coworker wrote this one. It's a truck fire versus it's a fire truck. It's a very nuanced difference, but I think it was a cool example. And so now maybe we'll see a difference in performance by label. So we can see, again, humans do pretty well across all 3. And even breaking this down, same thing. We get a better, more fine-grained understanding, but models are still really struggling. They're basically at chance performance. Then we have one other thing I want to dig deeper on. These are the visual labels. We have 3 here. The one on the left, we called pragmatics. These are cases where it's a bit more debatable what the right answer might be. So the kid with the magnifying glass looks at him versus in B, the kid looks at him with the magnifying glass. It's a bit tough who has a magnifying glass. Could be the kid, could be the adult. Then in the middle, series. These are cases where the images change very minimally. And I like this one because, again, it requires a deeper reasoning for the image. And the last one are symbolic cases. These are very cute little kids' paintings. These are ones that differ than the training data that models typically see. So doing the breakdown, we do see that humans take a really big hit in pragmatics, which lets us know that's a much more challenging category. But again, we see that the models are still basically at chance performance. They're really not doing a great job. And these are some of the state-of-the-art visual language models, and they're still really struggling. So the takeaway here that we can have is that models tend to struggle with more complex visual reasoning. And we should see this when we have really strong benchmarks. So this is a place where we'll know. If your benchmarks are showing your models are amazing at human performance, maybe there's something missing that you need to dig a bit deeper into. So that was the first question of what makes a good benchmark. And then next, I want to tap into what makes a good evaluation metric. So back to another example. My question here is there a banana in the image, yes or no? Do we have thoughts? It's a tough one because we can't really see the image. Yep, so we'll do one more. Here's the image, yes or no? Yeah, also hard because there's no question. And what's interesting here, if you have a good evaluation metric, your model should have to have an image and text. And this is something that's also missing. We've seen this in NLP, in vision language, in computer vision, where shockingly enough, models on some benchmarks can get super high scores without actually paying attention to the image and the text. And I'll dig more into this later. So quickly, I want to just go through how these metrics generally work in generative models. If you have an image that was generated by something like DALL-E, Stable Diffusion, Midjourney, and you have some text, so maybe a dog catching a frisbee, and in an embedding space metric, the model takes the image, embeds it into a high dimension, takes the text, high dimension, and says how similar are these in the embedding space, and gives you a score. And so if you're familiar with clip score, with the clip model, that's probably the most common one. It's a really quick, easy way to get a score for an image and text. What we're asking is, do they match? Then there are also, the second class are these visual question answering metrics, or VQA metrics. So again, we have some text, a dog catching a frisbee. We'll use a language model, maybe something like Llama, and get a bunch of questions. Is there a dog? Is there a frisbee? Is this the jungle? Is the dog catching the frisbee? We'll pass these to a VQA model. And again, we're asking, does the image match the text? We're doing it via questions, and we get a score. These are the two common ones: embedding space-based metrics and VQA-based metrics. And so what we did was we defined 4 criteria. We said a good metric should first pay attention to the question. It shouldn't be able to ignore the question and just guess. It should pay attention to the image. So it shouldn't be able to ignore the image and just guess. If you're giving us a new metric, it should give us some new information that other metrics don't already have. And then lastly, it should be really robust to shortcuts. And so we'll dig into these. And so first, we look at 4 metrics. I'd say the names aren't as important, but these are just pretty common ones that if you're doing evaluation for text image models, you're probably using. These metrics all, again, image, caption, and they give you a score. So for our first experiment, we wanted to know, are these metrics sensitive to text properties? And to do this, we looked at a couple different properties of the captions. We looked at their readability. This basically approximates the grade level of the text. Their syntactic complexity, so you take the caption, you make a big parse tree, and the bigger the tree, the more complex. And then the last one was just length, number of words. And we found that the metrics did correlate with these properties. So generally, longer sentences had lower scores, which we expect. Sentences that were more complex had lower scores, things we expect. So we felt like, okay, these metrics are pretty good at paying attention to the linguistic properties. Next, we did the visual properties. So what we were looking at is a sentence that is more concrete, so it has more real words, it's less abstract, it's not telling you to make an image about a person thinking and daydreaming. So more concrete. Imageability, that's if I give you a sentence, can you imagine it in your head? Can you sort of create a thought about it? And then the number of objects. And our question was, as they become more concrete, more imageable, and have more objects, do we see higher scores? And we didn't. And this was kind of curious. We were like, are these metrics just ignoring the image altogether? We weren't entirely sure. We dig into that later. Our next experiment, we wanted to know if the metrics were introducing new information. Because I think we probably would all agree that AI is a really booming field. There are new papers coming out every day. It's really rapid. And I think it's exciting to make new metrics, but they should be good in giving us new information. And so, oh no, I think I got rid of it. Oh, sorry about that. I had a little chart. What we saw basically is that they correlate really highly with each other. Each new metric is not actually introducing new information, which wasn't great. And then our last one, we we wanted to see whether they are robust to shortcuts. So thinking back to that example where I showed just the image and we just guessed yes or no, we basically formalized this. And so to show this more clearly, we have the 4 metrics. Each one is one of these plots. The original unmodified scores, so does the image match the text, is in blue. Then next what we did is we just randomly shuffled all the images. So I take the text, I give it a random image, and that's in orange. And we see the scores drop a ton, which is good. That means that there is some attention paid to the image. Then in green, we randomly shuffled the text in the caption for embedding space metrics or in the questions for those VQA-based metrics. And we see that there's really not a huge drop. So comparing blue to green, we would expect that if you're getting like basically gibberish text, that there's a change, but there's not a ton, which is a bit concerning here. Then in red for the VQA-based metrics, so that's the bottom 2 and the top right, we asked, what happens if we take away the VQA model and use something much simpler? And we do see a decent drop, which is good. It does show that powerful models are necessary here. And then the last one in purple, this is one I really like. We ignore the image completely by just not giving it to the model and only giving it text. So we took just a powerful language model to do this. And we see that there's not a huge drop, especially for the bottom right. And the bottom right metric is actually the most recent metric. So those blue and purple lines are really close. And in some cases, the purple lines are even higher. So there's something going on with these metrics here. So they consider the images to some extent, but they're still a bit brittle, which tells us that we definitely have some way to go in creating new metrics. So back to our 2 original questions. The first question was, what makes a good benchmark? And what we thought about is that it's really the benchmark design. It's making sure that models are paying attention to the image and the text and can't just guess. And similarly, for the good metric, you want to make sure you're introducing some new information and that you're robust to models just guessing. And so I should say that I love this field. I love evaluation because I feel like you can really answer some cool questions. And so if there are any questions here, definitely open to listening and chatting, and I'll open the floor.
So who has question for Candace?
Thanks for the very nice presentation. I think it's indeed very important to think of the benchmarks. Maybe I missed it, but I was wondering if you consider as well the relationship between the object, like distance is a very simple one. The bias is, because indeed I think like I saw in clip that far or close to doesn't matter. What matters are like the objects and not necessarily.
Just to make sure I'm understanding, is that the distance in the embedding space or like within the
No,
image?
like in the question, sorry, asking if 2 people are close or far.
Yeah, good point. Yeah, I'll hop back to that. So I'll just repeat the question, so just make sure I'm understanding as well. Is there any, or do any of the questions consider the distance of the objects within the image? Yeah, I think that's a great question. That would definitely be relevant for any prompts that ask things like, or that say things like, a person to the left of a couch. Like in that case, we would definitely check whether the person in the image is to the left of the image. And there are also some new metrics that are coming out that are looking at things like putting a bounding box around each object, so running object detection first and then measuring the distance. I think, yeah, it's a great question, and it'll be, I think I'm curious moving forward how we do it. I think one challenge is, like, what's a good example? Like right now, am I to the, I guess my right, your left, am I to the left of the podium? Yes. I'm still to the left, yes. Still to the left, maybe not anymore now. And so I think defining what that distance is like an open question as well.
Okay, thanks.
Thank you very much for the wonderful presentation. Yeah, so I'm quite curious, thinking internally. So you work on the responsibility and social theme. I'm quite curious how things work within the team and stuff. So for example, you query different models and try to see their limitations and where they flaw, etc., and evaluate those. How does that feeling work even as a team? If, say, for example, you're querying a model, for example, Llama built by the company you work for, How do you resolve those? Do you have to go meet the persons, or you just work independently away from them and you just publish your papers?
Yeah, I think it's a great question. So I'd say in general, so at Meta we have sort of two different AI teams. So we have one that's called Fundamental AI Research, or FAIR, and that does more exploratory work. I'm on that team. The other one is Gen AI, it's generative AI, and they're the folks who work more on the product side. And so I think on the exploratory side, it would be more like an open question. We would test a bunch of different models. So for instance, like here you can see we test tons of models. And then similarly, I thought I had a slide. I don't have the models listed. We test a lot of different models on the exploratory side. So I think our questions are more like less like meta model specific and a bit more open.
Maybe just a very general question. How do you see the future of generative AI? Because what you're describing is really about the bias of generative AI. Do you think we should have an additional layer of maybe compositionality of the image? Or how do you see that being solved at the large scale problem? Because it's gonna last forever, right?
Yeah, I think that's a great question. I think one way I see things kind of changing moving forward will probably be through the data. I think like we're at this place now where we essentially web scrape to get such large data sets. It's very convenient. I think it's brought us a lot of really great results. So like those images from the very beginning, like all of these models came from web scraped data. And it makes sense. It's easy to get and it makes for great models. But I think we will get to the point where we'll have to be a lot more intentional in how we collect data. So it may come from synthetic data generation. Maybe we'll work on having more like compositional prompts that then create these nice images. But I think where we are now is we probably can't just rely on the noisy web data and then hope to have better compositional reasoning.
So you're not only advocating for more data, right? More data, but also something else missing, right?
Yeah, I think more data and also better data. Yeah, so again, it might come through like recaptioning. I think is a pretty big thing people are doing now. You scrape the internet, you take the text, and then you pass it to a big vision language model, and you get better captions, and then you train on that. That's one route. I think people are looking at creating more images as well. So the images can have more sort of like a complexity within it. So the images even can be ideally a bit more diverse. So they're not creating images like this exclusively. So I think that's probably one way. I think there are also people who are considering like within training trying to make changes. So maybe you do something like you modify your loss function and you incorporate something that maybe is compositionally aware. I like that side a lot too. That's another potential route.
Awesome, thanks. Oh, question there.
Thanks for the great presentation. So most recent benchmarks are using generation to evaluate models. What are your thoughts on this? Like, are there any perhaps better alternatives?
That's a good question. Yeah, so most recent benchmarks are using generation, just to summarize that. And I think one reason we really like that is, so in the metric space, we essentially have two camps. You have human evaluation, where you have a person that's checking each image, does it match the text? That's just time consuming, which is why we, to your point, are using a lot of things that are generation based. And I think it's great that we can do things automatically and get great scores. The one challenge is just that we are in some ways dependent on the generative model. And like within NLP, like pretty much every language model is going to struggle doing some generations. So like on the question side, like when we give the language model some text and have a generated question, there have been some papers that have come out showing that these models struggle with some more complex text, and this is across the board. So you give a much longer, more complex prompt that's less sort of standard, you might not get questions that make sense. And if your questions don't make sense, when you do your VQA, then it's just gonna kind of propagate forward. And so, yeah, I think I definitely understand why we do generations. It's very convenient. I myself use it like every day. But I think we'll get to the point where we're gonna need some specialized models to make this aspect better. Hopefully I'm answering your question.
Awesome. Thanks a lot. Let's give a round of applause again to Candace. Thanks. So a few words. We're going to end the morning session right now. One word for the people that have poster or spotlight or both. Please before leaving, come and see us to check that you have your poster here. Normally they are already set up, a number of them, but so you're responsible of checking that. Another word is that we're going to resume the workshop at 2 p.m. We'll try to be on time. Can I have the screen back? Thank you. And finally, about the mentorship lunch, it's going to show. So we had 17 replies to the form that we closed because there was enough. We wanted maximum 4 people per speaker. So with all the preferences that you've selected, there was Fabio here, Fabio Pizzati, that ran a very complex model to find the Nash equilibrium into all this. And this is the result of the assignment. So you'll find your name, come downstairs there, and the speakers will be there, and you can eat with them and enjoy that time. And I think I want to say also to reassure the speakers that everybody is happy with that assignment. Everybody got a speaker they wanted to talk to, so no one was left out. Okay, see you at 2 p.m. I agree, Aisha. There is a problem in the assignment, Fabio. There is one name that is duplicated, or that person filled the form twice. I don't know. Okay. So everyone that filled the form, just come. Yes, otherwise Aisha will jump in. She seems to be eager to jump in. So anyone that filled the form, just come downstairs there and we'll find the small problem there. So upon verification, it's confirmed that it's Fabio's mistake. No, that's a lie. It's my mistake, apparently. So I will fix that. Who's the sneaky person that just registered right now when we say that it's full? Someone just registered right now. Okay, the assignment is correct now. I think it was just copy-paste mistake on Pierluigi. Luigi. Okay, and yeah. Isen, where is Isen? I saw you, Isen, around. Isen. Morta, Grace. Um, yeah, it's an email, so I removed the at gmail.com, but Rosaline, Rosaline, I was talking with you seconds ago there. So you have already two. You have already two. Oriane, you have already three, right? Um, Loyani will be adding. You have one. Okay, so that's not normal. Oh, you have two already. Cool. Okay. Uh, it's weird because I saw other people, the other ones that I know, I don't know where they went. Okay, so anyway, I mean, you have two or three each.
Didn't hear your name or you're not here. Hi, sorry. For the remaining of you that didn't hear your name or your name is written and you're not here, we're going to head to the lands. So please come along and we're happy to discuss with you. Si vous voulez au français, ils peuvent dire le nom, mais on va déjeuner. Venez avec nous. Chacun d'entre vous, vous pouvez trouver les personnes avec qui s'associer.
All right. I think each of the speakers, you already have at least two or three with you. So I think you can go and they will follow. Yeah, let's do like that. Tout est bon pour toi? right. Candace, you have yours? Cool. Okay. The group of Orion is leaving. Candace at the same time, and right behind, Vicky here, and Pierluigi. Have a good lunch. Can you hear me? Okay. Can you hear? Can you hear what I say correctly? Okay. But we don't hear you on the speaker. It's very long even for me to walk. So just so you know, we're waiting for the audio engineers to arrive. Can you share? Tell you. All right, so everyone, we're going to start in a few minutes. And Daniel, you're visible on stage now. Can you say a word, Daniel, to see if we can hear you?
Yes, I can do so.
Perfect. Everybody can hear in the auditorium. Cool.
Okay. Is it okay if I put off the video, or you want it on, at least for now, until Q&A?
You can leave it on for a few minutes, 2 minutes, and then after, when the video starts, you can switch it off if you. So I can introduce you. Right now, we just see the profile pic. Cool. Yeah, for the introduction, it's much better. All right. All right, everyone. Okay, I guess we can resume the workshop for the afternoon. So for this afternoon, we're very happy to have Daniel Omeza with us, but remote. So Daniel was working in University of Oxford. He just moved to the US, so he could not come on site to Indaba. But this time we have prepared a lot. He was nice enough to pre-record the presentation in order for us to be 100% sure of not having any internet problem. But Daniel, you'll be there at the end for the Q&A. So a few words, he was postdoctoral researcher at Oxford Robotics Institute in UK. And Daniel has been working a lot on autonomous driving and explainability of autonomous driving and how to make model outputs reasoning of their action. I'll definitely let you talk about it better. But we're very happy to have you here, and we hope to have you next time in person. So let's give a round of applause for Daniel, please. So we can start the video, and Daniel, if you want to switch off your camera, that's okay. I'll use that time to say that people that have posters and are not seeing their posters on the boards, please come to see one of the volunteers or organizer of the workshops. We're just there. All right.
Hi, I'm Daniel, and I recently joined Loc10 as a senior research scientist. Before this time, I was a postdoc at the University of Oxford, and most of the work I'll be presenting today were done while I was in Oxford. Thank you very much for the opportunity to speak at this workshop. I'm really excited to talk about the provision of explanations for responsible autonomous driving. Just to provide a bit of background, explainable AI in machine learning community has mainly been discussed around the context of model debugging and model reverse engineering, to improve accuracy of model and to study their failure modes. So we have a composition of functions with many parameters, and we need to be able to easily figure out why and when this function is erroneous. Explainability becomes very important in this kind of setting. So explainability is conceptualized to be either intrinsic or post hoc. It is intrinsic when the model themselves are interpretable. For example, the decision tree models, we have the linear regression models, they are intrinsically interpretable. So it is post hoc when the system concerned is opaque or black box and requires a separate mechanism to explain its decision. And you have examples of multi-layer perceptrons and the rest. So under the post hoc explainability, we would have model agnostic techniques, and we have model specific techniques. So model agnostic techniques, they are not tied to a specific kind of model. They are able to explain different kind of model, but this is going to be post hoc. So after the model has been trained, then we develop like a proxy model to explain the underlying model. And it is agnostic when this proxy model can explain different kind of models, and it's model specific when it's only targeted towards a particular type of model. And when we talk about scope of these explanations, so explanations could be local or global, or explainers themselves could be local or global. They are local when they are only able to explain just a specific prediction, and they are global when they are able to capture the overall behavior of a model and provide explanation for such. These days we have this new concept called mechanistic interpretability, which basically sits between model specific and local and global type of explanation. So you take basically a specific model, you try to open it up and see how it works, and then provide either a local or global explanation of for that model. In the context of autonomous driving, explanations are very useful for many purposes, and one of those is to facilitate trust and confidence in the stakeholders, and it could as well be used for debugging purposes and help assist accident investigations, and as well assist policy makers to make useful helpful decisions when reviewing regulations and policies. But I have mainly focused on using explanations as a proxy for capturing how the confidence of people can increase when they have explanations. So we want to see how we could provide explanations to help users better calibrate their trust effectively on AV technologies. So many work exists and around this area of explainability, especially in the context of self-driving. In the past years, we have seen people applying techniques like GradCam over machine learning models or deep learning models to be able to create a heat map over images or over videos, driving videos, to see which part of the traffic scenes are quite important for the model. And examples of the method that we use in the context of driving are the CAM, like class activation maps. You have the GradCam as well, that's gradient class activation maps, and several flavors of such. And people have also as well leveraged attention mechanisms to not just not just using the activations, but actually using attentions to see which parts of the input is very consequential to the decisions that the model is making. So we basically have NLP method as well, where we have textual explanations accompanying all of these saliency maps, attention maps, and heat maps that are created. Of course, you agreed with me that having just heat maps sometimes do not pass the message, but it's really nice to have these heat maps accompanied by textual natural language explanations. So there are methods that have that have been developed to provide or accompany visual explanations with textual natural language explanations. But the problem with all of these methods is that they suffer from generalization problem when presented with out of distribution scenarios. And this work, all this work I've just talked about, most of this work have happened before the surge of large language models and VLMs. So what do we need? Maybe we could think about leveraging inherently interpretable techniques to provide explanations for driving decisions, and one of such are tree-based representations. So we in one of the work we've done, we basically conceptualize like a traffic scenes in form of a tree, a decision tree, where we define the road rules, the observations and the actions, and we can traverse this tree to provide an explanation for a decision. You can think of it like a behavior tree. And we are able to base our explanations on this tree and provide like natural language explanations for what's happening. But to concretize this, so this is just a high level overview, but to concretize this, I'll just walk you through the process. So we actually need to collect data, because for you to be able to interpret a scene, you need the scene as well. You need the scenes in the first place, right? So we need to collect some data. And so we basically collected this data from London, driving around and annotate this data, and then we need some kind of representation as well. In this case, it's going to be a tree-based representation to just build like a behavior of how the vehicle from the data we have collected drove, and we can basically predict actions and provide explanations for the predicted actions and assess these explanations. So as I said earlier, we did the first step. We deployed this ego vehicle in London and collected a lot of data. We had a driving instructor who drove this vehicle and then was making commentary as he was driving, so we could learn from the way an expert explained his thoughts and intention and his driving behavior, and then we could leverage, we could use the insight from this explanation paradigm, to build our own tree-based explainer. So this is snippet from the.
With the cyclist, you see he's staying away from the curve because he's got better road surface. Now I'm on the bend here, so I'm going to move out a little bit early, but not put myself for the overtakes. I've got the bus and the bollards. There's a lot going on there. And I've got another bus on the other side and the truck coming. It's just easy to hold back, let the cyclist take his position. The bus is moving out now. Can't stick it out far more than it should do, so I'm just going to move out a little bit. And now the bus is indicating. So he's going round from the rock, which I'm assuming he's going around the cyclist. So the cyclist moving different speeds. We've got a car coming up. He's going to hold back to see if he's going to go for the overtake. He is.
Yeah, so basically, I just stopped it because of time, but that was explanation for a very complex situation where you have a cyclist in front, a bus in front, and oncoming traffic, and the driver was trying to like explain his thoughts, his plans, and what he was, and the situations around him. So what we did after we collected all of this data was to do some conversational analysis on the driving commentary, And when I mean driving commentary, I mean the transcribed audio data we got from the driving instructor, and we basically observed like a style in his explanations. So he announced his observations. For instance, he'd be like, "Hey, there's a traffic light in front, and there is a car in front of me," and then announces his plan. That's what's going to do, and then he makes reference to the road rules that informed the plan decision. And then once he implements his plans, he just starts making remarks about what he sees in the environment. So in terms of the style, different type of explanations present from the analysis that we did, we saw that factual explanations were kind of predominant. For instance, like, I'm stopping because, so you provide like a fact for whatever action he was doing. And then we have contrastive kind of explanations where he provided explanation like, I did not do this because. And then he also had counterfactual style of explanations where if I had done this, this is what would have happened. And so we wanted to see if we are able to generate a few or a subset of this type of explanations as well using our tree-based representation. So the next step was to do some data annotation where we have we just have multi-level labeling scheme. For each bounding box, we are able to add different labels describing the class of the object or the actor, describing its location with respect to the ego vehicle, and describing the action as well of the agent or the actor, and also indicate whether this actor was a primary influence to the current action of the ego vehicle. And we also try to indicate whether the driving instructor made reference to this actor in this particular scene, and then the road type as well. So this is a very rich multi-level kind of labeling scheme that is very useful, to learn how to train models and also to, do some kind of explainable AI research. As a concrete example, samples from the annotated data sets were obtained, and these samples were transformed into a tabular data set where features were road lanes with values describing the agents on each lane. So this tabular data set was then used to train a tree classifier. This model was able to predict driving action with up to 75% accuracy, and then we developed an explainer algorithm that obtained a representative tree from the ensemble of tree models, and the explainer traverses this decision tree to generate intelligible factual and counterfactual explanations. So let's go a bit deeper. So using the obtained representative tree, I want to explain how the explainer generates explanations. So as you can see, we do have the root node here, and you basically ask the question, is my plan to stop or not? So if the plan is not to stop, then we go to the next node here, and from this node we basically ask, is there an actor, an agent moving on this lane? That's the ego vehicle's current lane. If an actor is moving, definitely the lane is free, so we move ahead, or otherwise we're going to stop. If the lane is free and vehicles are moving, so we ask again, is there a green traffic light, or is there a traffic light that is green? Yes. If yes, we keep moving. Otherwise, if the traffic light is red, we're going to stop. And so we can now traverse this tree from the root node to the leaf node, and use an algorithm called local increment, or some other kind of algorithm to get contextual, to get what we call contextual importance value. And so with these values, we're able to set a threshold and just sample from the different nodes, just a few subset that we think are the most influential for the prediction. And then we can, decode the conditions along those selected nodes to natural language and present it as explanations. We could also do counterfactual. What we basically do is hey, what do we need to change for us to obtain the stop actions. So what we basically do is to just do backtracking, and then we go to the parent node and say, okay, maybe the traffic light has to be changed to red, but we don't have control over the traffic light, so we cannot change traffic light to red. So all we basically have to do is to go one level up again, and then find the common and go one level up again and see, okay, what do we have to change for us to obtain the stop action. So we basically need to get an actor in front of us that is in a stop state, and then we have to stop behind that actor. So following similar procedure, we could just use the criterion here. This is a critical node here that will be a candidate for a counterfactual explanation. Once we negate the condition here, we are able to provide counterfactual explanation for how to obtain the stop action. And cool, so that's how the explanations are generated from the tree representations. And so we have some results. Here is a sample of factual and counterfactual explanations for 4 driving actions along with entropy scores. So the S values here basically represent entropy scores. So ego stops due to traffic light. If you see on the left, the figure A, so agent stop because of traffic light, and then we have move actions. So with the corresponding explanations, basically the entropy score tells us how confident the model is, or the explainer is rather, for the explanations that it has provided. So we use the BLO4 and the ROH-W metrics to quantitatively assess the generated explanations against some ground truth reference. And the letter S is basically the entropy score. And in this context, it represents the level of uncertainty of the explainer for a generated explanation. And on the right is the distribution of the entropy score for the explainer. So BLO score and the ROH-W score are higher when the level of uncertainty is low. So when the level of uncertainty is low, that is, the explainer is more confident and then provides better explanations. You would notice that the explainer had the highest performance for the stop actions, and in like manner, the uncertainty level of the explainer is lowest for the stop action as well. So we did some kind of qualitative analysis where we randomly selected 12 short driving video clips showing the different ego actions. We presented these videos with their corresponding generated explanations to 12 human judges, all with driving licenses, and they drove in the UK. So we asked the judges to rate both the factual and counterfactual explanations on a correctness scale, maybe incorrect to correct, and factual and counterfactual explanation for stop actions had the highest ratings for correct explanations, and the lowest rated factual and counterfactual explanations were those for the right lane changes and the move actions respectively. So the model was not able to predict lane changes correctly as it did for stop actions. Now, what are the challenges of this tree-based approach? So one of the challenges is that the tree basically over-rely on annotated data sets from perception, and for you to make any prediction, you have to pass it already annotated data set, which doesn't look scalable in the real world. And we also note that tree models can grow very quickly and become too deep and sometimes overfit, so you have to do some kind of pruning method, and at some point, that also impact accuracy or performance. Another option is to explore scene graphs, basically graph representations. And we know that AV perception systems are quite good at detecting objects in a road geometry, but they do not explicitly capture inter-object relations. And this is very key to understanding complex scenes at a high level. So scene graphs are quite useful for addressing problems as these, as they are able to model spatial and temporal relations. So a scene graph acts as a distilled representation of a scene and can provide aspects of interpretability or explainability. So what we did is to basically create a data set of scene graphs, and we kind of generated a spatial-temporal scene graph based on annotated videos. And the videos that we have used in this context of this work was the one from roads. They call it road awareness data set, which has a very rich annotations of different actions of actors in the video, and the allocation similar to the data set that we collected as well. And so we're able to create varieties of graphs that represent each frames in the video. So to augment this scene graph, because at some point you would have the same scene graph for a couple number of frames, so we want variety in the kind of scene graphs that would have. So we decided to use both node and edge-based perturbation methods, so where we randomly drop nodes and permute the edge labels. Next, we kind of pre-trained a graph encoder network to learn embeddings in self-supervised manner. And so we utilized graph convolutions and self-attention poolings and LSTMs to learn representations from scene graphs. And we decided on using contrastive learning, where the goal is to basically maximize mutual information between two augmented instances of the same scene using contrastive loss functions. So basically, we want to to maximize the mutual information between two augmented graphs for the same scenes, and then we see how how far they are apart using a contrastive loss function. So we basically use attention mechanisms to interpret and explain future driving actions predictions, and of course this was the downstream task after pre-training. We compared our self-supervised method with a fully supervised baseline, which shared the same network details but was entirely trained on labels. And you would see that the self-supervised method outperformed the baseline when trying to correctly predict future actions. Like I mentioned earlier, so we entirely trained the encoder without labels, and we used the embeddings and the context vectors, including the hidden states, as input to decoder. And we did some kind of fine tuning with a few labels, to predict some, driving actions. But in the fully supervised baseline method, we use the same architecture, but the only difference is that now there is no self-supervision. All of the training, process, involved the use of labels. And as you can see, this baseline did not perform as well as the supervised, the self-supervised approach. Yeah, which is quite impressive. Okay, so here is an example action prediction and heat map explanations. And so, like I mentioned earlier, through the use of attentions, we're able to map back the attention scores back to the input graph, where we highlight different nodes and their importance. And we could as well, see that we have, if you check this axis, you see that the vehicles closer to the ego vehicle are quite more important compared to the other vehicles that are parked or quite far away. So we combined all of these tree-based and graph-based method, and we to create like a demo that we have shown in different settings. So this is an example. And the next is the
problem with the video. I guess.
All these models are context. Why not use them? We've seen a lot of work along this line, and even some accompany this with vision-based model as well. Examples are Drive GPT-4, Adapt, Drive Everywhere from NVIDIA and a couple of them. So some of these models leverage the multimodal capability of GPT-4 to achieve explainable driving, while some use features from video encoders and LLMs to achieve explainability. But I want to note that, however, generalizability could even be better, and that's one of the problems we set out to address in the work I'm about to talk about. I also want to note that explainability is quite different from interpretability, although they are similar concepts. While these models provide textual explanation, they are still black box because they are not interpretable. But the good thing is that we can use these textual explanations to reassure confidence in autonomous driving, assure the confidence of stakeholders and passengers in autonomous driving, and enhance human-AI collaboration in a shared autonomy context. So they are still useful. Where we would not use this method are contexts like accident investigation, where we want the model to be 100% correct, and we want to be able to verify that the explanations are 100% correct as well. So in that case, it's very hard for us to use explanations from LLMs because they could hallucinate. In our recent work, we proposed RagDriver, a retriever augmented in-context learning method for multimodal large language model that achieved state-of-the-art introspective driving explanation performance on the standard benchmark dataset called the Berkeley driving dataset for explanations. And it has well demonstrated exceptional zero-shot generalization capacity to unseen scenarios in our new driving dataset, which comprises of video sequences narrated by a professional driving instructor that I described some slides away. Here is the architecture of our method. So given a query or a prompt comprising a video of the current driving scenarios and its corresponding control signal, the process starts with the input query being fed into the retrieval engine. So the retrieval engine searches within a memory database for driving experiences that are similar to the current scenario, and it returns relevant in-context learning samples which are appended to the original prompt. A multimodal large language model processes the current query and the retrieved in-context learning samples. The model makes various predictions, such as action explanation, action justification, and next control signal prediction. To achieve a multimodal LLM, we had to perform some trainings to align both the visual and language features. So let's zoom in a bit into this. So in the pre-training stage, we used language bind to encode the videos. Language bind is a transformer-based visual encoder based on BIT vision transformer. We adopted Vicuna 1.7b as the base LLM backbone model, and Vicuna is a chat assistant trained by fine-tuning Llama 2 on a user-shared conversations. We then designed a cross-modality projector, which was basically a two-layer MLP. We froze the weights of the visual encoder and the LLM and trained the weights of the MLP on the subset of BIDAL 10M dataset, which contains about 3 million video caption pairs. And so this helped us achieve alignment between visual and language features by basically projecting the pre-trained video embeddings into language tokens understandable by the LLM. We then used cross-entropy loss as the training objective. So in the second stage, we unfroze all the weights and tuned the multimodal large language model using curated in-context learning demonstrations. So we see that while the state-of-the-art large language models exhibit zero-shot capability, our ablation study shows further improvement when specifically trained on curated ICL demonstrations. We constructed a multimodal instruction tuning dataset with structured ICL examples based on the Berkeley driving dataset for explanations. This resulted in about 16,000 video question and answer pairs. And the dataset is tailored to support 3 distinct tasks, each represented through question-answer pairs in natural language. One thing to note is that the action and the justifications are both represented in natural language. This applies to as well the control signal prediction as well. They are all textual. This is possible because we have a distinct mapping of numerical values to specific tokens within the large language model dictionary. So this makes the representation of control signals in natural language possible. Here is a prompt sample with a pre-printed ICL example, and the rest sentence is what we expect the model to predict. You would see that we commence the prompt with contextual system information that just provides contextual information about the task at hand, and then the next is the ICL example, which comprises of control signals retrieved from through RAG, speed, curvature, acceleration, cost, and the prompt, and then example responses and the example prompts. And we have a couple of examples of these ICLs, and then we have the actual query, which provides all of the informations as well, like the speed, curvature, acceleration, and cost, and then poses a question, and then we expect the model to provide a response to that question in natural language, and on and on like that. So it's going to be like a chart. To perform the retrieval, we first leverage a lightweight MLP projector of the same structure as the one described earlier to project the heterogeneous video and control signal embeddings into the same hybrid embedding space through metric learning. And we adopted a triplet loss function with Euclidean distance, where a P and N defines anchor, positive, and negative data samples, respectively. So the positive and negative examples are separated using text similarity scores, and of course that's the general TF-IDF scores. And so this basically the TF-IDFs of the actions and explanations and as well justifications in the BDDX training set. So this forms a kind of metric space such that similar driving actions are close together, and vice versa. So retrieval is performed through vector similarity search, giving a query vector the cosine similarity between the query vector and each vector in the database is computed, and subsequently we consistently select the 2 most relevant driving samples based on this similarity score. These samples basically represent the entire reasoning process from contextual informations to question answering pairs. We used BLOW 4 and C and Meteor M metrics to evaluate action explanations and justifications on the created BDDX text set. RAG driver outperformed other benchmark models, including the Drive GPT-4, a generalist model. And for generalization evaluations, we created another data set for evaluating zero-shot generalization. We collected this data set while driving in London with a driving instructor, just the one I explained initially in the talk. And so we basically use this our own new data set now, which we call the SACS data set to test for generalizability. So we discovered that RAG driver also outperformed existing models on zero-shot generalization evaluation after we did this evaluation on this new data set that we collected by ourselves. And yeah, these are the results right here. here is the qualitative results. So at the left is the annotated ground truth, and on the right are the predictions. So this plot shows the comparison between our method and some baselines for the in distribution and out of distribution generalization settings. The vertical axis is basically the CIDR score for the explanations. And despite the performance gap between these two settings, our method significantly outperforms all of the baselines, including ADAPT, which is a specialist baseline, and as well as Drive GPT-4, which is a generalist baseline. We use the root mean square error metrics to assess the predicted control signals, including both the steering angle and the speed. We also present this metric called tolerant accuracy metric, which is denoted by A, uppercase A, alpha, subscript sigma, rather. And this basically represents the accuracy of predictions when binarized within a tolerance threshold of sigma of the ground truth. And from our ablation study, we discovered that using both video and sensor embeddings in our retrieval strategy, as opposed to using only visual similarities, yields better results. And in context examples, both at the train and inference time yields better result as well. As a closing remark, we want to note that explanations are critical for trust formation in automation, especially in self-driving. And different kind of representations, especially those that are inherently interpretable and expressive, are quite useful but are limited. Examples are trees. Trees are useful and provide clear, simple explanations, but they are limited as they depend likely on annotations. And graph are as well expressive, but they don't generalize as much. And VLMs can generate possible explanations, but we cannot verify the explanations that they provide because these explanations are provided by black box models themselves, which are susceptible to hallucination. So we know that well-formulated in-context learning process could improve accuracy and generalizability. And finally, closed-loop testing is required to verify practicability of the described VLM's method. And that said, this brings us to the end of this talk. Thank you very much for listening, and happy to take questions. Hi, I'm Daniel, and I recently joined Log 10 as a senior research scientist.
Maybe not recently. All right. Thanks a lot, Daniel. Can we keep the screen on to share Daniel? Daniel should be online. Are you there? Yeah, awesome. Okay, so thanks a lot for the talk, for having recorded the talk in advance. That's appreciated. It avoids having the internet issue. So, there are any question in the audience? All right, one question there.
Thank you very much for your presentation. My question is, as we're trying to gather your data sets, that is the driving data set, what limitation did you experience or come across, and then how did you solve those limitations? Thank you.
Yeah, good question. So I think one problem that we all know regarding data set collection is annotation. And so you collect all of these data sets, and you can't do anything with it except you do some annotations. And yeah, it's a really rigorous manual process where I had to do a couple of these myself, and get a couple of colleagues as well to assist, and did this for several days and several hours. So that's one of the challenges that we faced. The other challenge is basically trying to interface with the different teams. Like we have this vehicle that has a lot of sensors that are being fitted on it, and the engineers in the institute are responsible for the effective functioning of this vehicle and ensure that all of the sensors are working during trials. And trying to interface with the engineers and ensuring that everything is in sync is also one of the challenges that we faced. But I think, yeah, in the end, we had very good data set. We had voluminous as well data set, which we are releasing very gently, like in phases. And we have used some of this subset of this data set for some of the experiments that I described in the work. Another challenge was basically getting a driving instructor. So a driving instructor, for the kind of driving instructor that we wanted somebody who can do commentary driving, not just instructing a learner driver, but somebody who can drive and at the same time speak about what he's doing. And the police force is notable for this kind of exercise. They drive and then they report the situation as they drive. So getting this kind of instructor that can do commentary driving and while driving, I think was a bit challenging. And well, we got him and we were able to get meaningful data from the whole trial.
Awesome. Oh, there is another question.
Okay, thank you for the response to my question. But going forward, is there no way to solve this issue of annotation manually? Because I work with a video data set for human posture detection, and I also experienced the same issue. Although, unfortunately, I was the only one working in that area, so I did the annotations myself. So going forward, is there no way, maybe like a code that can be written to solve that? Or,
yeah,
I don't know.
I mean, that's a good question. Yeah, I agree. It's a very painful task, but a couple of people fall back to kind of self-supervision. So we just annotate a few of the data sets, and then we kind of learn a model that can do the rest of the annotation somehow. Yeah, so and also try to look for options where you don't completely depend on labels to train your model. So these are some of the options that people consider. And I think that with the advent of VLMs these days, yeah, I think that there are some. It depends on the kind of annotation that you want to do. If you are, for example, in the driving context, there are some models that are already fine-tuned on the driving data sets, and you could just leverage them and say, create a caption for me for what is happening in this video, and then you can use this as a ground truth, and perhaps you have some human evaluator who basically goes back to do a check to ensure that everything is correct and proper. Of course, so it makes the process faster and a bit easier. But yeah, so these are some of the techniques that people use today. So we could use AI as well to do annotation, yeah, especially VLMs that have been fine-tuned on the data set at hand.
All right, thank you. I still have another question, sorry.
Let's see.
It's my area of interest, that's why. Another question is your data set available online? And if it is, how can we get the link to the data set? And then the last question is, what's your future plan on this area of research?
Okay. Yeah, so in terms of availability of data sets, so we got, yeah, there is the radar version. The radar version of the data set is available because the data set we have a lot of modalities from LiDAR, from radar to commentary to bounding box annotations and different sort of it, and the CAN bus signals from the vehicle. So the radar version of the data set is online, and if you check SAC's data set from the ORI, you should be able to find it, and there is a paper about this as well that has been presented, I think, at ICRA recently. So, but plans are in place to like roll out the explanations ones as well. In terms of next line of research, I think that exploring how to leverage VLMs in the context of driving is a very interesting problem and interesting task, and I think there's still a lot of work to be done along that line. And you want to think about how we could, I mean, it might be very difficult to integrate all of these methods directly right now in real-world systems because they are still, for example, the work we did, we have not tested in the closed-loop system where we see how the vehicle actually drives in the real world when we use this model. So we can't guarantee that's going to work, and it's a very safety critical situation where we don't want to take any risk. But one line to think about, or one area to like explore, is seeing how to use these kind of methods to facilitate driving education, maybe in simulation where you have a driving content, and you use VLMs to like guide learner drivers on what the driving rules are. Of course, the consequences in this situation is less grievous compared to when you deploy them in the wild. And that's one way to think about it. And instead of allowing the models to like take over control or to drive the vehicle, you can also use the model to like for navigation purposes, like sat nav. So because okay, there's this, you can observe X, Y, Z on this scene, and so based on the situation, we advise you to like slow down, or we advise you to. So you can also use some telematic data, and inform learner drivers or new drivers or drivers that have moved from one location to the other where the traffic rules have changed, and they're able to like get some kind of help from leveraging methods like VLM. But I think a still existing problem is the fact that we cannot trust them 100%. Like I said earlier, we need inherently interpretable like techniques, not just techniques that can provide text as explanation, but we need techniques that are in themselves transparent. And that's why I started from the tree-based method that are in themselves transparent. And so if there is a way for us to leverage very symbolic approach to action prediction or explanation, I think that would be the best way because that's basically interpretable and transparent.
Okay, thank you a lot. I think we'll stop here for the sake of time. Let's give a round of applause to Daniel again, please.
Thank you very much. Yeah.
Daniel, thanks a lot for this presentation. And I invite everyone that has more questions for Daniel to contact him directly via email. So we're going to move to the spotlight session. So we have 3 spotlight presentations. Please come on the front row, the people that will do so there should be 2 presenters on site. One is told me that couldn't come, so I have the video. There is Matthew. Matthew is around? Okay, cool. So I've identified the 2 of you. Who want to start? So, Matthew is standing up, so let's go, Matthew. Yes, so these are the 3 presentations. Normally, the spotlight presentation is supposed to be 4 minutes. Good luck for those that I've seen that have 15 slides. Good luck for that, because I'll interrupt you after a while, so please try to keep the timing, okay? And after the spotlight, we will have the poster session, so just saying that there is no Q&A with the spotlight, but you can interact directly with the speaker right after, even for the paper that is where the first author could not come on site. There is a colleague that is here to answer any question. You okay? Is the screen working? All right, so first we have Matthew Janical-Géré. Sorry if I don't say your name correctly. presenting a study about RGB UAV. You're going to have to explain what is UAV for the audience in case of image segmentation using FCNs. Okay, the floor is yours.
All right, good afternoon. My name is Matthew Cherry, as you had said, from Malawi. I work as an intern at the University of Malawi. I just finished my undergrad last year in October. My presentation is on image segmentation. Specifically, these are unmanned aerial vehicle images in remote sensing. And these images were captured using an RGB sensor. Focus is on RGB because RGB sensors are the most widely used and the most cheaper than multispectral sensors. So we wanted to see if we can still achieve the same results that people get in remote sensing when using algorithms that depend on multispectral sensors for the other bands like the near infrared, the microwave bands. So RGB poses a challenge when it comes to segmentation because the spectral severability that most of remote sensing algorithms rely on is limited when it comes to RGB. So we're trying to find models that can still achieve the good results for segmentation of images so that they can be used in either agriculture, for example, in yield estimation, in precision agriculture, in land use analysis as well. So what we did was we collected drone imagery. We collected images from an area in Malawi, that is Zomba. After collecting that data, we stitched it together to form a mosaic, and then we patched into 224 by 224 patches, and then we labeled that data. The target classes were 5. We had trees, buildings, barrens, vegetation, and also maize as a separate class out of the vegetation. We target maize as a separate class because maize is one of the major crops in Malawi. So whenever there's no maize in Malawi, it's like there's no food. So we wanted people to be able to raise the models for estimation of maize and analysis on that. So we developed models, the units models, depending on ResNet V2 as a backbone, the mobile nets, the VGG19, the efficient net, also raised attention units, and DeepLab V3. Mostly we target the small models because of efficiency. We wanted the models that can be used by everyone in their local machines. So we preloaded the pre-trained net weights from ImageNet on these models. So we fine-tuned them on our data set. And we evaluated these models using intersection over union, the accuracy, recall, and precision. So these were the tests that we got. The top performing models were ResNet V2 based model, that was the first one, seconded by the MobileNet V2, and then the VGG19. The top two models, the attention units and the DeepLab V3, seemed to be too complex for this task, so they were just overfitting on the data set. While those three generalized very well on this data. This image just shows an example of the segmentation that we did using the ResNet model. So where there's the brown shows that's the barren, the red one shows that that's the maize. So the insights that we got from this research was, we know that we can still utilize these small efficient units for segmentation, for segmenting RGB images, so achieving the same results using these cheaper sensors. The selection of model also depends on your task and the trade-off of accuracy and computation. For example, the MobileNet performed very well on this data set, but it's a small model that can be utilized in low-end machines. You can also use the ResNet, which they performed very well amongst all the models, but it do require some processing power. So our next steps are to try and optimize the models better. When I try and use the latest models, for example, the transformers, so when I try and develop efficient transformers and utilize them on this task, also when I try and generate some synthetic data to augment our data set, currently we only managed to label 200 images, of which 150 were used for the training and 50 are used for evaluation. So when I try and use automatic segmentation, for example, using the segment anything model to try and segment our images to further improve our models. Thank you.
Thanks a lot, Matthew. All right, please keep your question for him and go interact with him at the poster. He's gonna be there. Thanks a lot for that. I'll put your computer. So now for the next presentation, we're gonna have Iman Hamzawi that will be talking about bio-inspired learning rules to neural architectural search. Okay. Can we share the screen? Okay. All right. Let's give a round of applause. Iman, the floor is yours.
Okay, hello everyone. Thank you for showing up. Today I'm going to be presenting our framework, BioNAS, that incorporates bio-inspired learning rules into neural architecture search. So a little bit of context. So the human brain is very similar, shares many similarities with the way neural networks, either with how the connections are weighted and plastic, or also
put it a bit farther away.
Okay, or with having many individual neurons that learn non-linearly, and also in terms of structure. So convolutional neural networks learn different representations across the layer, just like the brain vision system. So the problematic that we have is that bio-inspired neural networks usually don't yield in high accuracy, and neural architecture search current methods consider only the architecture in the search space. And also, backpropagation is very good with optimism loss, but it's not biologically plausible. So the goal is to, of course, achieve state-of-the-art bio-inspired neural network accuracy and incorporate the learning rules into the search space. So for a little bit of context, most of the methods that have been used come from computational neuroscience, like which are mostly Hebbian methods, and they have advantages like they are biologically plausible, but mostly unsupervised or semi-supervised robust, but they do not scale well on complex tasks. So for artificial neural networks, there are many more biologically plausible learning methods, but so we can classify them into alignment methods and target-based methods. So alignment methods, the most famous ones are feedback alignment, direct feedback alignment, and sign symmetry variants. And we have other methods such as DRTP and PEPITA. And also we have the forward-forward algorithm, and both target-based methods usually rely on two forward passes. So the advantages of these methods is that they are useful for custom ASICs hardware and are more biologically plausible, and they are robust to adversarial attacks. But they suffer from certain limitations, such as not being scalable on complex tasks. And for example, feedback alignment suffers from vanishing and exploding gradient problem. So what we propose is not to use just one feedback method and use different learning rules across the layers and mix them. And the question we asked ourselves is like how to mix these learning rules to learn different representations in a smart way. And this is why we thought about doing neural architecture search, and we propose BioNAS. So we consider the search space as blocks as usual, but for these blocks, we set different learning rules. And these learning rules, we have taken them from the package BioTorch. And for feedback alignment, the matrix that is used instead, in backpropagation, we use the weight transpose matrix, but in feedback alignment, we use a random feedback matrix. In the sign symmetry methods, we use the sign with some variants. And for the search method, we use a baseline of darts, which is like one of the fastest, and even faster EGNAS for complex tasks, such as even bigger, to scale it for bigger data sets, such as ImageNet. And the search process remains classical. And for the results, we highlight here that mixing the learning rules using neural architecture search performs better than using the same learning rule or other state-of-the-art methods in biologically inspired neural networks. And also, we try to see what happens with this learning, and it's a bit similar to using regularization. So yeah, I think I'm gonna receive your questions at the poster. Thank you.
Thank you, Iman, for this presentation. I know 4 minutes is really short, right? I know, yeah. Even shorter when you're on stage. By the way, since we're talking about computer vision, I'm looking for the next one at the same time. Yes, since we're talking about computer vision, like this has been removed, but in the last year when you had Spotlight, for example, in CPR, so top tier computer vision conference, you had 2 minutes 50 seconds, if I remember, or 150, I don't remember, to present your work in front of the whole audience. So that's really short. Some other community, like computer graphics, they have 30 seconds or 50 seconds to present their work. It's really, really short, it's challenging. Thanks a lot, and we'll listen to the last speaker, that is Austin. You have the poster outside, but Austin could not come, so we'll listen from there.
Methods based on framework for answering our work on ARJAPOS, a framework for animal pose estimation methods based on VHR network architecture. Over the past years, traditional methods like GPS trackers and accelerometers have been used to monitor animals in the wild. An example is shown to the left of an elephant tagged with a radio collar to track its movement. These tags can obtrude animals' movement, causing physical and behavioral interferences. To curb these intrusive ways of monitoring, camera traps have risen over time, and they use computer vision to monitor animal behaviors non-intrusively. Animal pose estimation goes beyond conventional animal recognition by obtaining the particular joint of this animal, providing us with more detail, but this also makes a need for a model architecture that can be able to capture the diverse skeletal structures of animals, from fishes to reptiles to amphibians to mammals and birds. This becomes of significance on many fronts, such as examining if an animal is in pain as it moves by examining the paw movements. How we do this, the network ingests an input image A and processes it through two primary branches. A high-resolution network, HRNet, the branch that extracts detailed spatial features, and an attention branch, which applies self-attention mechanism to capture contextual information across the image. For each joint, the model outputs a heat map. We end up with a collection of Dirac deltas where we compute the loss function as the mean squared error between predicted and ground truth heat maps. To evaluate the performance of our model and its accuracy, we use the percentage of correct key points, PCK at 0.05. This is when a limb is considered detected if the distance between predicted and ground truth is less than 5% of limb length. We trained and evaluated our model on all animals of over 850 species. We ended up with a 93.1% accuracy, as shown in Table 3. We went ahead and compared the model performance of the initial VHR bird pose model and our model when tested on birds only. And our model outperformed the VHR bird pose, where ours attained 95.2% as in Table 1, while the initial publication has 90.2% as shown in Table 2, indicating that our model generalized better due to the auxiliary classes, mammals, fish, reptiles, and amphibians, as they share common vertebrate traits. During evaluation, we encountered that our model struggled with images that contained multiple animals or animals quite far in the frame. One way to fix this would be to take a top-down approach, localizing where the animal of interest is and then fitting the pose model. This was shown to be useful as it fixes the scale and reduces the XY search region to an enlarged area around the detection window. An example of how we did it was by using an out-of-the-box YOLO V8 model for animal localization, which detects the sheep, and the pose model to detect the joint, making it possible to do multiple animal pose estimation. Thank you for listening. You can scan the QR code to get started with our work. We deploy the train model on which you can be able to build on top of it for any downstream analysis.
All right, let's give him a hand. Again, the poster is, sorry, again, the poster is there. So with a 20-minute delay, it's not so bad. We're gonna go to the poster session, and they're gonna be the coffee break kind of in parallel. So we have a bit less than an hour for the poster session. Next presenter is gonna be 4 p.m. and 10 p.m. And it's gonna be Vicky around, and then we're gonna have the panel and the announcement of the award, of course, at the end to keep you alive and keep you entertained. All right, let me remind also that for all the speakers, you have to look at the posters. I know you have no break, sorry for that. You have to look at the poster and give us feedback of which poster you want to receive the award, and so that we find a consensus or something. All right, thanks a lot, everyone, and let's go see the amazing posters that are outside. There are about 20 posters outside on computer vision. Let's give a clap to the people that are presenting poster, please.
Test. Hi.
right, everyone. I know that some are still speaking outside, but we're going to have to resume. Let's start. So now we have, for the last talk of the day before the panel and the decision of the award, we're going to have the chance to have Vicky Calogueton that flew all the way to Dakar to present, and she's going to be talking about multimodal for story-level understanding and generation of visual data. Actually, I'm just reading the text. But I want to highlight that Vicky is assistant professor at École Polytechnique. So in France, she's affiliated with a couple of teams, and she works a lot on multimodal learning. She's being, you know that she's our speaker. You know she's the speaker now, and she's being asked to take a picture. I think it's the spirit of Indaba. All right. So yes, as I was saying, she has a lot of work, very visible on multimodal data. So we're very happy to have her. And while you start your talk, I'm going to go grab the people outside. Thanks a lot, Vicky. Let's give you a round of applause, please. Thanks.
Thank you, Raul. This is a very nice introduction. I will spend the first 1 minute stalling around in case somebody else wants to come. So I want to thank Raul. It's the first time that we actually meet, and I am very glad that it's under these circumstances because I'm actually very happy to be here. It's a great community, and I have been just introduced to it. I am sad for not having done it earlier, but I am very grateful for having done it finally. And I think that from now onwards, I will be around. Thank you also to all the organizers for this amazing job. And like here, there is a good friend of mine, Benjamin Rosman, that I would like to thank as well. And also thank you to you all inside and outside for being here and making it a very nice experience. So today I'm going to discuss a bit of my recent research at Polytechnique that is around multimodality for story level understanding and generation of visual data. This is a lot of fancy words together that probably they mean nothing to you. Hopefully, like in 5 minutes, they will mean something. If not, then I failed, and I'm sorry. If yes, then great, yay. So first, some things about me. As Raul said, it's been 4 years now that I am an assistant professor at École Polytechnique. This is in France. This is in Paris, like great city, very beautiful, like lights and all. Before that, I was in Oxford, where I was a research fellow. And many, many moons ago, I did my PhD somewhere between UK and France, in Edinburgh and in Grenoble. And that's it. And generally, my research agenda is represented by this slide. So overall, I work on multimodal generative AI with 3 particular axes. One is visual generation, the other one is video understanding, and the last one is medical imaging. So I will say a bit more for those later on. You don't hear sound, right? That's interesting now. Yeah, I didn't connect the cable with the sound.
You guys, does this look like something the girlfriend of a paleontologist would wear? I don't know, you might be the first one.
Yes? Did you hear enough? Yes, it seems to be okay.
We'll discover how Mac works. So either way, somewhere down there are the subtitles, where this is a scene from a TV show that's called Friends that I hope most of you are familiar with. If not, this is 100 great hours of your life, where with multimodality, we are interested in understanding, for instance, what's happening in this scene. So we want to understand this type of low-level things, that there are some characters, that they are located in the apartment, that there is winter, for example, because of the clothing. Okay, not in this image, but somewhere here. But also, we want to understand some high-level characteristics. For example, that there is anxiety on what to wear, that there are some interactions, that there is a joke to diffuse a situation, and so on. So multimodality essentially connects all these different components like the video, the audio, the text here in the form of the subtitles or the voice, or the background noises, or the temporal editing structure of videos and so on, in order to reach a final desired output. Why does it matter? Because of the vast majority of applications that are directly related to it. For instance, there are surgeons that are being assisted every day by cameras or by automatic predictions that are popping into the screens that help them while they perform live operations. Or for fun, like for instance, YouTube, that we do what is called like text-to-video retrieval, that we every day we try to find videos online. Or for fun, like Wii or Kinect, and so on and so forth. And here we see such an example of this kind of modern application where we would have like this vision system, and it's able to actually localize the human in space and time, but also understand that there's like potentially somebody's drawing, and they are alerting that, and that they can be understood from several modalities, for instance, like the heart rate or the various processing of the water. Another example refers to automatic storytelling, where if we would like really to understand everything from a video, then we would like ideally to have basically an agent looking at the movie, starting the story and the true content of the video, and even suggest another video based on our interest. And of course, the most exciting application of today that we all know are like self-driving cars that have started working. So here we see such an example where we see the car. On the bottom, we see the 3 cameras, left, middle, and right. And the car is able to localize, there is a bicycle somewhere there, it's able to localize the bicycle and predict its trajectory and act accordingly so as to avoid the driver. So vision, sound, LiDAR, and several other modalities, as already discussed today, can help to that. So in reality, these are all very cool and all, because these are very nice, fancy applications that exist out there. But in reality, why does it matter to me? To me specifically, I have a 2-year-old daughter that I tuck every night to bed, and she doesn't want to go to bed. So every night we spend like an hour trying to say stories. So I am starting a story by saying, once upon a time in a farewell land, there was a dragon that was called Zoe, and she was different. And ideally, what I would like is that I have on the back, like on the back wall of the room, there is a projector or something that automatically understands the video and generates a visual illustration of what I'm saying. So it's about this Zoe, and like this is personalized because, for instance, my daughter likes the color orange or the color green, so the dragon is gonna be mostly green, and the tone like follows me, like the tone of my voice, so the video follows that. For example, if it's a bedtime story, then my voice will be sweet and slow. Therefore, the video should actually adapt to it, as opposed to a really exciting story while I'm trying to feed her. So basically, my whole research is within this story level generation, where on the one hand, I'm trying to have this type of long-term story level understanding, where I tackle this long-term understanding and multimodality, and then I'm trying to use the information that I'm learning here for text-to-video generation, where I would like to have this dynamic storytelling techniques and the text-to-visual content alignment. So I'm going to show some examples of these 2 different axes. So I will start first with video understanding. So the question that we are asking first is whether or not this is funny. So 3 tomatoes are walking down the street. Mama tomato, Papa tomato, and a little baby tomato. The baby tomato starts lagging behind. Papa Tomato gets angry, goes over to the baby tomato and squeezes him and says, ketchup, 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 ketchup. So this is a scene from Pulp Fiction that for most of you mean nothing, most likely. However, I have a little dog that is called Ketchup. So for me, this has been an everyday life that we keep saying ketchup and ketchup. So this was the motivation of this type of work, where we're really trying to understand whether a video is funny, yes or no. So this has been a work that first published a couple of years ago in ACCV and won the Honorable Bachelor Award with the brilliant students of mine, and was published this year at IJCV. And why does it matter? So there are several applications of this type of models. My favorite, I guess, one would be the second, that we would like to make more spontaneous and funny and real interactions with the machines, like we have Alexa at home or Google or Siri in our mobiles and so on and so forth. But it would be so nice that they are able to rack up a joke instead of replying, yes, the weather is 22 degrees tomorrow. Like, it would be so much nicer to have this spontaneity. So how do we do that? We start with a video. We get a bunch of information that we call modalities, and then we're creating a neural network that we are feeding it this information, and we are asking it to tell us whether or not something is funny, yes or no. So with related work, I'm not going to bore you with the details. The main point is that they're limited and imperfect. Guess what? And non-flexible, mostly because they are relying on text, whereas instead, we also exploit the raw modalities of videos. It's audio and the text that we can automatically subscribe. And we use self-supervision and we are exploiting the canned laughter of videos. So this is a video of this is an image of our model, where given some video frames, we extract some RGB information and we pass them through some transformers. In this case, it's video mascot encoders. And we are also extracting the audio that we are transcribing automatically to text, and we pass it through a modern LLM. In this case, it was Llama 2. And also, we take the audio in the form of spectrogram, the wavelet, and we are passing it respectively through an audio encoder. And then these three modalities, they go to what we call the cross-attention fusion module, that we are taking the union of all modalities, and the union of them supervises with cross-attention and self-attention with these particularities. And in addition to that, there is a classification loss, funny yes or no, and there is a self-supervised loss that basically says that modalities, we should explore the complementarity as well as the overlap of modalities. So if video says it's funny, then we should also make audio say that it's funny. So the comparison to the state of the art, we see here, this is our model, that we are we have this text that is, we also compare it to a bunch of state-of-the-art methods. So we are using it with phase, with audio, with text, so we can have several modalities as our method is scalable, and we're going to go to several details, and we outperform the state-of-the-art. And then in the updated version for the journal, we also offer into the wild exploration, where we further outperform the state-of-the-art, highlighting the effectiveness of our model. So I guess in this case, these are all videos, so you cannot hear the sound, which actually loses half its fun. Maybe I will just play one, we'll try. So these are funny moment predictions. So I'll try one. Do you hear this? Okay. I cannot really actually I mean, as much as I like, it's impossible for me to impersonate Chandler. So I'll just okay, now you stay out here and you think about what you did. That's a duck. That's a bad duck. So basically here we see that this is a joke that I guess you understand the joke, because we cannot say that this is a bad duck. It's like a bad I don't know, dog or something. So we see basically the modalities, how each of the modalities is contributing to the final performance. So we see here, for example, that there is this high pitch. Therefore, this audio, which is this pink part, is the one that discriminates the most and is able to tell us that this is funny. So I'm going to skip through all the other videos because we cannot hear them. And respectively, here we have the predictions that in reality they are not funny, and our model correctly predicts them as non-funny. So I'm going to skip through them because we cannot hear, and that's half the fun. We are also comparing to a chatbot, which means an automatic large language model. So we tried ChatGPT, we tried Llama, like Facebook, Meta, OpenAI, and so on. Like we tried several of them, so they are all in the paper. So here I have one, and basically what's interesting is that our model, just by using text, which means just subscribe the subtitles, performs significantly better compared to existing large language models. What we also see is that large language models, this F1 accuracy there, like no matter the prompt engineering and so on, that we tried several things, there are more in the paper, they still have like quite a good performance. Like they have 50% chances of saying whether or not something is funny, yes or no. Which is mostly because they have inherited knowledge of most of these famous like American TV shows like Friends, because they have read them through subtitles, transcripts, post reviews, and so on and so forth. So here we have some false positives, which is usually what we like doing, like examining the failure cases. So we have cases where we have this type of strong emotional responses that are expressed by a single wording.
Something else I might have said?
Weren't you the guy that told me to quit my job when I had absolutely nothing else to do?
So in this case, it's not so funny, but it's sarcastic. So these type of things are very hard for such a simple model to understand. I will skip again through the other type of video, and then we have false negatives. That means misdetections, basically, things that we do not detect. That we have, again, this type of subtle sarcastic comments with straight face and follow-up indications or inside jokes that require this type of long-term understanding. And here also a bunch of other examples that I will again skip them. And we also applied them in other domains. I will skip them because if you cannot hear, especially the people in the back, then it's a bit boring. So we also applied to a bunch of other movies that they don't have laughter, and we are actually adding the laughter when we think that this is funny. And here we saw just such an example, but I will skip through that as well. So in conclusion, we propose this FunnyNet into the wild network that is an audiovisual self-supervised network that exploits the audio, the visual, and the textual modalities and outperforms the size of the art and for various different configurations. Next work in this category of video understanding with multimodalities is movie question answering. That's a recent submission, that an ongoing work that we have right now. So with respect to the time scale of videos and how we treat videos, there is a massive issue. First, we start by having videos that operate in seconds, then we have some minutes, then we have some hours, days, years, and so on and so forth. So ideally, we would like to have models in our community that are able to work on and resonate at several temporal resolutions. However, in reality, what happens is that for text resources, there are several of these that exist that span over years somehow. Mostly, we refer to history books. But for video resources, if we want to have something multimodal, this doesn't particularly exist. And the only one that is the longer term that we could have, we start from instructional videos, and perhaps we can go to things that are like movies. So for this reason, there have been several movie data sets in the community that have been proposed. However, most of them that I don't analyze here are closed sourced. We don't like, because we cannot distribute with each other, and so on and so forth. So we are proposing a short film data set, which is we called SFD. That, as you see here, is a video data set that contains questions answers with 1,000 movies, and my mouse is lagging, and 5,000 questions. And the key thing here is that we are scraping actually channels online that are for free. So specifically, we're exploiting amateurs channels because they are actually using YouTube and Vimeo and all the other media platforms in order to share their work and gain visibility. And they don't fall into the standard copyrights, so we can use the videos and distribute them. So we have all the nice things, nice goodies that movies have, including the long-term interaction and the reasoning for characters and for events. And here we see such an example that when it comes to the standard parts in the community, which is like instructional videos, that has been the last couple of years, or egocentric videos that nowadays they gain more and more popularity. Basically, we don't have so much diversity. We have like the videos are open source, but their diversity is much less. If we see here, okay, and also they're much more boring, in my opinion. At least like seeing something from one person, like first person view. And also their temporal window is usually limited. They have like 1 minute, 2 minutes. How long will you show somebody like mowing the grass? It's, you don't even film that thing. Whereas movies, like they span over a longer temporal extent and they have this evolution of characters over time, that there is something happening. So we can actually learn more from that. So this is what we see here. So when we are comparing our proposed datasets with existing datasets from the various domains, so we see here that ours, in terms of average video length, is much higher, and with respect to total hours, is a good dataset for training, not for pre-training, I must say. And we are creating the story level questions and answers. We have publicly available videos. Then we performed an experiment that's actually quite interesting, that is what we call contamination or data leakage. So what does it mean? Existing datasets, especially movie datasets that showcase Titanic, guess what? All LLMs know how to answer how is Titanic story evolving, and if Leonardo DiCaprio is dying in the end, and so on and so forth. So this is what we term here with the word leakage or contamination, that LLMs have pre-existing knowledge of various things in our natural world, and that actually includes movies and this type of video content data. Therefore, creating datasets and creating methods using these datasets can create like these results that are not, that maybe they are skewed, they're biased, and they're not necessarily correct because they don't necessarily reflect the whole part of the problem. However, and this is what we measure here, so we do it for a dataset called Movie QA and TeleView. We do it with a gazillion models, like we also put Mistral, OpenAI, Google, like all the big companies, they're kind of there. Meta, and don't forget. And we saw basically that the higher the performance, the more contaminated a dataset is. Bigger models have more knowledge, therefore they perform better. So this is zero shot, we just ask the questions. And whereas in our case, our dataset stays quite low, like 20% being the chance level gets a 30%. Another thing is the questions with long temporal context that we saw here, how basically, like we just compare, in this case, like two state-of-the-art models. One is called Frozen by LM, and the other is called Yovi. It's not so important. What is important is the trend that when we are comparing at the shot level, scene level, and movie level performances, then we see that at the movie level we can have higher accuracy, which actually supports a longer temporal window. For example, when you say for the Titanic, what happens in the end, then you need to see the whole thing in order to understand, because there are back and forth things and so on. So we would like to have models that are able to operate at a short window, but these most models nowadays do, but also on a longer temporal context. And we have two major findings from our experiments. So the first finding is that basically here we are comparing accuracy. So we have multiple choice questions, only with vision, only with language, and only with vision language. And we are asking humans to evaluate, to see how easily they can answer the questions. So when we give them the actual video, 90% of the case they can answer the questions. When we only give them the transcript, this happens 70% of the cases. Whereas when we mute the video and we do a Charlie Chaplin type of movie, then 60% of the cases they answer the questions. And when we compare it to a bunch of models here, the difference, we see that the model that performs the best in the language world is actually quite close to the human performance only, language-wise. However, when it comes to vision, we see a massive gap between the performance of vision models as opposed to the best thing that humans can do. So essentially, what we see is that vision is much less evolved compared to language, which is actually in line with what you were saying earlier today, from a very different perspective. For the standard VLMs, at least the commercial ones, the famous ones that are out there. Okay, so also here that we see that basically no matter what, these performances are massively below the human, so that even for the multimodal case, we have 55%, which is lower anyway, and whereas the multimodal one is 90%. So this summarizes this part of the work, which is about movie question answering, that we propose this film data set that contains 1,000 films from amateur directors. If any of you is an amateur director here and would like to contain your film, please reach out and we'll be happy to do so. We can create questions. You can also tell us the tricky parts. We hope that this data set can actually help a bit the community with less contamination, with the opportunity of stories that evolve over time, with kind of longer temporal context. And we think that basically works that can work on this data set should focus on really the vision language part, because language by itself is quite advanced, as we can see. So this concludes this first part of the work that was about video understanding, and I'm going to say like a couple of works about visual generation. And I think I'm 22 minutes in, so I think I have like another 15 minutes. I will try to be quick because that's the last talk of the day. So I know that most of you want to go home, and we will do that afterwards. But for those of you that want to hear, then I'm happy to say more afterwards. So the first work is with a bunch of people, like many of them my brilliant PhD students that have currently under submission. That is a work that is mostly an analysis that does the following. So we all know, or I hope you all know, all the big models like all the big models that do text-to-image generation, like DALE. Yes? Somebody like nod? Yes, thank you. Okay. And anyway, so stable diffusion and so on and so forth. So most of these models, they use something that's called classifier free guidance. That here I have the equation of this, that I don't expect you to understand much, but this says that in order to generate something based on diffusion models, there is a lot of beautiful math behind it. If you are interested, we can discuss it later on. So there is this term that is the generation term. So that says, okay, generate something. And then there is this other term here that's called guidance term, which basically says generate something that is not only beautiful as the first term dictates, but also follows the text that we are having as input. So having only the first term, this one, will do something very beautiful, very artistic, very photorealistic, with very fine details, but it's going to be something random, just drawn from a distribution. Having this part actually makes it follow the text input. And there is this extra term, that is this omega, that is a term that is this guidance term that is used to control the magnitude. Basically, how much do we want to follow the text input, the condition, yes or no? So this typically is a hyperparameter. I will not bore you like with a lot of the results on the right, but what we need to know is that this is a hyperparameter that in practice we set it to 7.5. So if you don't know what you do, you put it at 7.5 in all models, and that works. But this is done heuristically. However, we performed some initial experiments, and we saw that don't having it stable over the whole generation process, but actually modifying it, can improve the results. So this is what this graph shows here. I'm not going to go into details. So what we are trying to do in this work is that we have this initial funding, and we say instead of having this omega, this stable, like static as one value, let's have it a function. And what function? We're examining two types of families. The first family are heuristic functions, and the second family is parameterized function. So for heuristic functions, we're just making a function of the time step in the diffusion process. So it's linear, cosine, and so on and so forth. And here we're examining the results. And we see in all the results, basically, that the functions that are monotonically increasing result the best. So there is a massive difference in FID. So the lower, the better. This is a bit counterintuitive. And here we see the results on text-to-image generation. And we see again that we have better balance between quality, condition, adherence, and diversity. And here we see some visual results of this nice thing that's like a stormtrooper drinking coffee in a Parisian cafe bar with the Eiffel Tower in the background.
So I don't know how much you can see because it's in the projector, but basically this is the baseline. This is a standard like stable diffusion in this case. It's a like open source text to image generation model. Here we have some of the, like when you replace this omega with something that's linear or cosine, it's monotonically increasing, whereas here we have monotonically decreasing and these other like non-monotonic functions. And we see that like this decreasing perform like very badly, even visually, not only quantitatively, whereas the ones that result to the most like visually pleasing outputs are the ones that are monotonically increasing, which is the ones that I'm zooming in here. So we see that for the prompt that says, for instance here, 2 birds flying in the sky in bad weather, then here we have the initial, when we have static, here we have linear and cosine, and here we have the zoom-in versions of the previous ones. And we see that this is good enough, but these two are, like the details are much more fine, we have a better quality, like we can see the peaks, we can see the, like much, first of all we have 2 birds instead of this thing, that's most likely 2, but it's not sure. The colors are nicer, the background is also much richer. And we also see it with diversity. So, for instance, if we see here on the top one, like we have this brown teddy bear lying on a sand with a hat, then even without looking at it, we can see that here there is much more diversity. So we have, I don't know, like something that is zoomed in on the face. Then here we have this hat, and we have from further away. This mouse is lagging a lot. As opposed to the baseline on the left, that the diversity, like even if we zoom out and we don't look at details, it's much lower. And then as a second thing, we are saying, okay, like we have these functions, okay, we examine the heuristic, but let's do some parameterized. What does it mean parameterized? That there is an additional parameter that comes from the GAD or from grid search in reality, a lot of GPU hours. And we do that because there is actually some related work that uses them. So we wanted to see how they compare to the other functions. Are they better or worse, or how do they generalize? So we examine this with this clamping, which is like this, can be linear cosine, but like in the initial generation stages, we just have a maximum, and respectively this, which is a parameterized cosine that, as you can imagine, this comes from a paper, it doesn't come from us. So we're comparing against this one. So basically what we see here is that, yeah, okay, this family, we examine this for several parameters, this C1, C2, C3, C4. So C2 performs the best, whereas here S1 performs the best. Okay, so this is for the sticks, sorry. So C2 performs the best, whereas if we see that for another model, there is the C4 that performs the best, and the S0.1 that performs the best. So basically what we want to show with this, without going a lot into details, is that these type of parameterized functions can perform much better. However, they do not generalize. So this means that for every new data set, every new model, every new training setup, and so on and so forth, then one needs to redo a grid search of the parameters and find the best parameter. So if one cares about efficiency, they should definitely not do that, or about generalizability, they should not do that. But if the goal is high performance, then perhaps this will be the best. And here we see some visual results. For example, you can see the one on the bottom, Big Ben made of French fries. So we have the baseline, linear, this parameterized linear with 2 parameters. And here we have the zoom-in version, and we see that indeed this one is much better with the parameterized compared to the one without no parameters. But as we said, it's in the cost of, at the expense of not having, not being generalizable. And we do this here also for the other type of family. We compare them with each other. But in conclusion, we are examining 2 types of families of families for functions to replace this omega, this static guidance, by something that is either heuristically set or parameterized set. And we saw essentially that the ones that are parameterized and monotonically increasing, they improve the performance. The code is one line. We have the code also line, and the parameterized one are actually much better, but they risk overfitting. And the last part that I'm going to present is this work here that, again, my PhD students, some
I'm very happy for them to work a lot for me. This is very nice. They do a great job. So this is a text-to-camera trajectory generation with character awareness. So this is, if you want to create a film or a story or a camera, then you will go into tools like Blender and so on that they actually are quite complicated to use. And let's say even the best of us that's able to use, then they will do something like what I'm doing here, if you see, that it's gonna look like nothing. So as you can see, this is a 3D generation of something that makes no sense. Like we see the camera being from the bottom, being from the side, and we don't understand exactly what's happening. We don't understand what this character is doing. So actually, for animation and production, for cartoon and so on, it's very important to have a correct camera placement that follows the story, because this is the one that conveys the emotions that the audience feels at the end. And that we can actually see here, that we can start with something like this. This is from Toy Story, that I have this. So I wanted to show basically the camera movement that is able to follow the character, that is zooming in and goes all around, and then you can also add this type of sound, like the music in this case, You Got a Friend in Me, and you can end up to something that is actually like visually pleasing and makes us all smile. I assume that if you have seen Toy Story, you smile with this type of scene. So anyway, having basically 3D cameras putting cameras in 3D environments is an exceedingly tedious process. So this is like just to show you how many clicks is needed, even for somebody that is an expert and knows how to do, like to place them so that they follow the characters correctly. And generally, a scene without editing, like the one on the top, is like basically the big challenge is that the way that the camera is positioned is the way that the filmmaker, the director, wants to convey the scene. So for example, if we had like the Star Wars scene that it says, "Look, I'm your father," no, something like this, and in this case there was "Search your feelings," no, and there was no zooming in effect, then we wouldn't be able to understand the tragedy of the situation and the pain in the characters' eyes and feel for them and actually be very much immersed into the story. So all these, the importance, motivations, intentions, emotions, they are conveying actually via the positioning and the positioning and the movements that the camera is doing. So what we are trying to do in this work is create methods and data sets that can help amateur filmmakers and democratize this type of filmmaking process instead of require like so many clicks, and for people like me that have close to zero artistic, I don't know, essence, like they are still able to produce something reasonable. So we do that by creating first a data set that is the data set we see here. So we start initially from a video, then we extract, we are extracting and doing this pre-processing like this camera motion, as you see here, and then we do what's called motion tagging. So we are mapping we are splitting every motion into something unique, and we are saying that, for example, here that the character moves right, then they advance forward, and so on. And we do that for a character, and we do that by estimating also the position of the camera, and we do that for the camera as well. And then we are generating a caption from these ones here, like the one that's on the right, like the camera tracks right while the character moves right, followed by pushing towards the character as it advances forward. So we are pairing basically a video scene with a textual description that describes the motion of the character and the motion trajectory of the camera following the main character. So in numbers, our data set that we called ET, Exceptional Trajectories, is the largest of its kind. It has cinematic content. It has controllability for characters and captions, and it's in the domain of movies. And here we see some examples of them. So for instance, here we have the camera tracks right while the character moves right, following by pushing in towards the character as it advances forward. or we have like, well, the character moves right and then forward, then the camera tracks right to follow the motion and so on. And in addition, we propose, this is a fancy architecture, we propose a method called director. So this was the idea of my PhD student, Robin, that it's actually a very nice name, in my opinion. And here there are the different configurations of directors, so I'm not gonna bother you with the details. These are like transformer-based diffusion, based on the diffusion transformer in different configurations with cross-attention and context learning and ADLN. And here we see the results where we see like basically what is a good trade-off between efficiency, performances, which one handles better sequential conditions, and so on and so forth. And here we see some nice qualitative results that we end up having with our methods. We examine several axes. So first we are examining the ability to choose whatever camera trajectory. So here we see that, for example, that we can move the camera in every direction. So booms bottom, booms top, and so on and so forth, given the same character trajectory. Whereas here we have, we saw that our method has this ability to generate these diverse camera trajectories, given again the same setting. So for instance, given the character moves right and the camera performs a boom bottom, then we can have several ways of placing the camera, and they can all be realistic. Here we see the ability to generate this type of complex trajectories. So while the character moves to the right, the camera stays static and pushes in, or respectively tracks right and remains static. So they're always the same scene, but a different camera motion based on what's written in the text. And here we just we saw that how well the character condition is taken into account. So we have the same scene, but we just mirror it. And we tried like this. The camera remains static as the character moves to the right or left. So we see indeed that the camera has this character awareness. So this concludes actually this part of the talk, and I think with time, like I have 5 minutes. Okay, I'll do it. Okay, I thought that I have another 1.5. That's okay. I'm good with time. So basically, I will say like maybe 1 or 2 slides about what's next. So. There are many things next. It's very hard to summarize them here. I guess one of the things is that I like myself is this multimodal self-supervision, that there are all these inherited emotional characteristics like audio, speech, dynamics, language, and so on and so forth that can actually help us understand what's happening and how to generate. So we can see, for example, here somebody running based on only some textual input. So anyway, in this case, we are just showing that exploiting audio can automatically tell us that this is high five because the character is actually saying, oh, high five. So basically, understanding this would lead to actually understand better what's happening also in real videos. Another line of work would be like towards this visual content generation that most of the current research, to my knowledge, is basically is amazing line of work that does this text-to-image generation or text-to-video generation. So here is an example. It's a quite old one. It's from a year ago, like from Make Video, that basically everything is rendered through text. So most works that exist even nowadays, what they do is that they transcribe audio to text and they do text-to-something generation, visual content. However, like the audio itself, like the pose, intonation, the accent, and so on and so forth, have much richer information. They have much more to offer. So one goal would be like to have this audio to visual content generation without having to go through text. Another thing, especially for the generation part, refers to this memorability. So according to like many cognitive science research, like story, emotion, and place are the 3 elements that actually increase our memorability of situations. For example, like all research on the 9/11 in the US, like the incident, like then they saw that basically people were starting like by remembering the place that they were when they found out the news. I was in my office, I was entering the bedroom, and so on and so forth. So I would like to explore this in the existing visual data, check how modifying each one of them can actually affect the memorability of a given video situation, and see how having this, having altering the stories or the places or the emotions can actually impact the generation accordingly. And my long-term goal, as I guess most researchers working on AI goal, would be for a unified AI where all these different subfields like vision, robotics, NLP, cognitive science, and so on, they work together towards a common grand goal. And thank you for your attention. And one last thing is that if you're interested in working with me or shooting or doing an internship or like discussing or anything, you can shoot an email at any time. We'll be happy to discuss further, either by mail or Zoom or in face or even like in person afterwards. Thank you.
All right. Thanks a lot, Vicky. It was hard to find the mic. Happy to take question. Is there any question there in the back? I can see that someone had a number of questions today, right? It's good. It shows interest. That's great. Yeah.
Okay, thank you for your presentation. And my question is that when we do on audiovisual speech recognition, what matters as of I think is fusion. So you have extracting audio features independently and then the video feature or the visual cues independently. So what do you recommend on fusing those two modalities?
Sorry, I didn't understand the question. It's about fusion, but...
Yeah, fusing those two modalities. I think it's multimodal, meaning that you have audio feature as well as there is also video, so visual cues. So once you extract both features independently, then how can you fuse or add those two features?
Okay, so I think that there are too many paradigms there. That's independent of my work, as you said. So there are too many paradigms. The other one is maybe three. So the first category is operating two different networks, independent, like one network per modality. So if you have vision and language, will be one network for vision, one for language. And then at some point, very later on in the learning process, for example, if it was ResNet, it will be at layer, 50, you combine them. This with transformers doesn't work like that, so you have encoder for one and encoder for the other, and then you combine the features later on. That's one paradigm. The second paradigm is that you do that a bit earlier. So you are extracting some information in the beginning from either modality, and then you're putting this information as input to a transformer that takes both modalities or like every modality that you want. So this can happen either with features, so it can be again one encoder per modality, and then you combine the features, but very early on, or it can be with tokens. So you just, which is more modern, I guess, that you take the initial input, you tokenize it, like you take your language, you tokenize it, and then you insert the tokens as input to transformer. They both have pros and cons. I guess the main con of the second part is that it's not scalable. Every time that you want to add modality, you need to retrain and to redesign and retrain. But at least it's a one model end-to-end. The disadvantage of the first one, I guess, I don't know, will be that it really depends on the representation power of your individual encoders. Does this answer your question?
It seems he's doing a thumbs up. If there is any other question, meanwhile, I have one small question about the short video understanding. I was really wondering, this is really a naive question, do we have a way to measure how much we rely on knowledge that is not contained inside that small short video? Meaning that when you're showing a video of Friends or How I Met Your Mother, I actually know how to interpret what the character is saying. Is it something that we can measure with human studies?
That's a very good, interesting question. I would be very happy to learn about these cognitive science things. I have very limited knowledge on this. I would say that it's it's more about our understanding of the world, that we know that the world is like this, and when a character, I don't know, when somebody's approaching us smiling, most likely they want something good. So it's this type of personal like priors and biases that we have. I guess it's like it will be very hard to evaluate, but super interesting.
Some question there? I'm running.
Thanks for the very nice talk. I had one question regarding the work about generation. So you mentioned how the parameters are not generalizable from one method, one model, and one data set. What do you see? How do you see a solution to this problem? Like, which direction would you go to try and prevent that?
I would go towards models that are generalizable as much as possible. So myself, I'm a big fan of like zero thought and examining things on data sets we haven't trained with models that we have never seen before, seeing performances, because this makes it more interesting. Yes, sure, you can still have a good performance on, I don't know, like benchmark A, because you need that in order to progress your research. But the nice part is to examine the failure cases, and the failure cases are not, in my opinion, not only on the benchmarks that you are examining at every time, but also all the ones that you do not examine and they don't perform well. So in my opinion, this like we need models that perform well across different benchmarks. Like is distillation a way to do that? Is I don't know, having a lot of training data another way to do that? Is synthetic data? Like, I guess I wish I had an answer. The answer.
Thanks. Makes sense.
Yeah, thank you very much. You didn't talk much on clinical data, the clinical modality, the medical modality. How do you incorporate this into your work? The medical aspect of the model.
Sorry, I really didn't.
The medical modality.
The multimodality, yes.
Yeah. You didn't. Can you say a little on that? On the medical aspect of the mode. The medical.
Okay.
Yeah, exactly.
Okay. Oh, so I didn't saw anything there, but the general research where I do there is basically how can we leverage multiple modalities for forecasting. I work on forecasting. For example, one work that we have is with doctors with a hospital Necker in France, that there were some patients that had undergone liver surgery, so renal surgery. So they had transplantation, so they changed liver. And these patients, they do exams after the transplantation, 1 day, 2 days, 1 week, and so on, to see the progress. So what we are trying to do is, in addition to the various medical imaging data, for example, MRIs, that this is standard for a lot of medical data, is how to integrate other things. Other things would be time series, like the heart rate of the patient, can be the notes from the doctors, can be also like type of tabular data. For example, the creatinine level is 52, the age of the donor is 42. All this type of data that are somehow incorporated into like the brain of the doctor when they are making a call to say, is the liver failing, yes or no? Then if we can also include this to a model, in addition to imaging data, then we can have more reliable predictions to help doctors. So mostly my work is with actual hospitals and medical data that is really about the forecasting. Like there is a problem and we want to integrate, in addition to some visual data, some tabular, some textual data, and how do we integrate them to help like having high recall in this case means that we can be more sure to notify doctors in time.
Thank you.
thank you, Vicky, for the presentation. So I have one question. We know text, visual, and auditory data are different. So how can we combine them in real-time process system to create coherent narrative? So I want to say, what are the main challenges to overcome on this process?
What are the challenges of which process, sorry?
Yeah. So can I say it in French? On sait que les données textuelles et auditives, tout comme les vidéos, sont différents. Maintenant, comment faire pour les combiner in real time pour avoir le process de narration dont vous avez fait?
Okay. So the question is how can we combine multiple modalities, for instance, vision, text, and audio, in real time, so that we can have this, so we can have this real-time processing, like of an output, like for example, is this funny, yes or no? Can I answer a question, yes or no? Or this.
Yeah.
Okay. I said it in English also for. All right. So I guess this goes back to maybe this question of your colleague as well, that there are several ways to combine modalities together. One is at the very beginning, and then there are several ways to combine them up to the end. So one can imagine having them like directly translated to something that is common, like common nowadays means feature embeddings or means tokens, usually, but not necessarily. And then having a network, like your favorite CNN, your favorite transformer, having them all as input. So this is usually one of the ways to do that. At the same time, when we want to have some like real-time processing, I guess the challenge is, which is part of your initial question, if I understood correctly, is that data are missing. So if I'm speaking right now and you want to recognize, is he funny? Yes, he is. You need to catch my jokes. But if you do not get that and you cannot get my accent or my voice, then you cannot understand this. So there needs to be a way to maybe generate the content that is missing on the fly, or mask some inputs, like with dropout options or whatever, so that data that are not paired together, like the network can still function even if you have this type of missing data. Does this answer your question?
Yeah, thank you.
Thank you. If there are no other questions.
I think we'll keep the question for offline question, and we have a small session still, so let's give a round of applause for Vicky.
Thank you all.
Thanks a lot, Vicky. Actually, you don't have to leave stage. You can stay on stage. We will have a very short panel with the speakers. So please, speakers, come on site. We are lucky to have right now Joyce that is joining us right now. Just Naka Tumba Nabende. I hope I'm saying it correctly, roughly. Yeah, so she's also joining us in the panel, so please, you can either stand or sit as you want, and you can pass the microphone. So we'll remain a bit short, but I still want to keep that opportunity to discuss all together. And my first question is not really maybe a question, it's also the opportunity for you to present. If you want to sit, you can. Joyce, my first question is for you. Can you tell us a bit how it is? So you're head of the scientific head of the Makerere AI Lab. It's actually a lab in Uganda, in Kampala. You have a microphone, right? And so it's a lab that is getting more and more visible. The last person I met is actually a personal story. Was when I traveled in Uganda a couple of weeks ago. I met someone randomly in the countryside, and he was working on research, and he said, oh, I'm there to try to collaborate with Makerere, but they become so famous, they want money right away because they have so many contacting them. So can you tell us how it is in Makerere AI Lab to do computer vision? How do you manage to do computer vision? What's the unique aspect? Maybe the complex aspect of it, but also the success, because you had a number of them.
Yeah, thanks. I would need like a whole afternoon, but let me try and keep my answer really short. It's good to hear the story about the lab. So I think for us, how we've managed to do computer vision is the need from the experts who need the tools that we are doing. So for example, if I look at the agriculture experts, part of the work that we're doing in agriculture is image phenotyping, where they really are trying to harvest and breed for better varieties of crops, cassava, sweet potato, for example. Maybe one good example is sweet potato. I don't know if, I think we have it here in Senegal as well, where they're trying to do and run sensory panels. So they do breed for different varieties, they harvest the sweet potato, and then they give it out to a panel of 8 to 10 people to test and say, I think I prefer this variety over this variety. But that's very expensive, you can't do that. And so they came to us and said, can you be able to visually take an image of the sweet potato and, be able to rate and tell that this sweet potato is sweeter than the other sweet potato using computer vision? It sounds like a very simple task, but it is not, because how do you tell? People are used to telling it in the mouth. Now you have to tell it from an image, which is such a difficult task. But we've managed to work with them to understand their side of the story, the agricultural specialists, and then build tools with the help of the students that we have in the lab that can actually be applied. Another example is healthcare, where working collaboratively with the experts, we've understood, because most of the technologies for screening in low resource settings is imaging, like you're using a chest x-ray, for imaging, or if you're doing cervical cancer screening, it's all imaging. And over time, we've, through the collaboration that we've had with them, it's really, really helped us to understand the value for the tools that they're developing. That's computer vision, trying to help us with building out annotated data sets and helping to build the models out and test and evaluate with them. And so this close collaboration that we've had, because when we set out, we are only a lab that does computer science models, but we want to build for them in their field. So this close collaboration with the experts, either in health or agriculture, has really helped us to have the success for the tools and the technologies that we are developing. Thanks.
So agriculture remains the #1 topic on computer vision, right? Okay. Actually, that allows me to connect with the research of the other speakers. We're in an interesting era, right? We're at the era where we have this foundation model that we can use, and we very often we highlight the complexity and the computational cost of training this model. But it's also fantastic opportunity to use this model and at very low cost, maybe fine-tune them to be working very well on smaller data set, or even completely unsupervised. So maybe I can target Oriane right away with that, if you want to answer.
Yeah, thanks. I think it makes a lot of sense to let people who have money and a lot of compute do some hard work, and then to come and to exploit it in ways that maybe wasn't meant for that. And I found that in recent work with object localization and supervised object localization that I presented this morning, you can really exploit features and characteristics that were not meant to be there. The model was not designed for that, but the model learned a lot of things, and we have, I think, great opportunities in exploiting that and getting the information out, and for different problems. This morning I presented 3 different problems around object localization, but you can do lots of stuff to adapt for your specific problem with one layer. I was using one conv11, less than 1,000 parameters. You need a small GPU, and I was training it on with 2 hours, I think, on 10,000 images, and that's it. So with no annotation. So basically, there are, I think, lots of opportunities, and I think it's very interesting. And when the competition is so ferocious between big labs, big industry, there are great places where we can find actually very small and cheap problems that we can solve. And I think that other people don't think of because they have means and they can do other things. So thinking a bit aside, and then we can find nice solutions, I think.
Hello? Okay. I wanted just to say that another thing that we can do with low resources is to explore like emerging fields and where the studies can be on toy data sets and you can experiment with really a customer GPU like 3090, for example. My paper that I presented before was all trained using two GPUs, standard GPUs. So I think that would be also another way to do research, also relevant research, and without having to use clusters of thousands of GPUs. I wanted just to say that.
Okay, thanks a lot for this answer. Actually, I'm very interested in that direction because I think they're really fantastic works that are getting out now that requires extremely little computational power, and I think maybe what was said in the past that you cannot do computer vision with low resources, it's actually something you can do now. You can build on the shoulder of giants and do that really at a very high level. So that's something I find interesting. So like extending a bit the question of the foundation model, when we talk about generative AI, and Candace, you've been talking about a number of it in your talk, we see all these different bias of the generative AI, right? I mean, we definitely they relate to the data being used, but is this like what is your feeling? Like, do you think like the data is the only solution? I mean, only gathering data. What else can we do? And maybe that you can then pass the mic or connect. I mean, is there a need of African foundation model? I mean, or should we keep these current trends of having like this universal model?
It's a really good question. Really good question. I mean, so I guess we're at the stage now where these foundational language models and vision models are being trained basically on just like internet scrapes. And it ends up being mostly like the global north, it's the west. And so I like your idea actually of focusing on training a model, particularly on maybe it's data just from Africa or data just from South America. I think this is a good perspective. Because I think where we are now, at least, it does seem like data is kind of where we're leaning toward. I have seen some work that I think is exciting that's coming out that's focusing on post-training, because like you mentioned, you have a couple companies who are training these large models because they have the resources. So maybe the thing we can do is, okay, great, the model is trained, now we'll make changes at inference time to try to be more diverse. So like one thing we tried to do was, like it was a generative model as it's generating images, basically each step you try to be as different as possible from previous images. And we found that helps a little bit, and that's just one of like many works that people are doing. So maybe we can do this post-training. It would be exciting if we could just really leverage the existing models, either that or to your point about focusing more on data from here.
So I just want to maybe re-extend my question. What about the fact of having several foundation models? I mean, at the end of the day, we do have different language when we discuss. Culturally speaking, we have different way of even at looking at the scene when we look at the landscape, and you have people from Asia, Africa, Europe, US, they see different things. So what's your maybe feeling about that? And I'll give the mic to you, Joyce, but feel free to jump in.
Yeah, thanks. So I think to kind of have them work, I think the culture, the context, I think is dependent. And I think you touched a bit on the data. Should we improve the data? Should we change the data? I was actually reading, because I had the NLP session, so I was asked by us, so I had to read a bit, and I saw a paper about scaling for foundational models, and they said that the more you increase the data, the worse it gets, I think, for a particular case study that they were looking at. So if you increase the same kind of data, you're just going to increase the probability that the model will be able to see the bias that is already existing. So I think, and then they were like, it's not just about the amount of data that you keep increasing, because that increases the bias that's existing. So I think also doing this at inference level, I would agree, would also be a good way to do it. But then also, trying to understand the data before the training and doing that investigation quite exhaustively to bring in the cultures, as you've mentioned, because what we see is different from what is in Asia, is different from what is from another continent. So I think those have to be, I kind of feel like it's a balance of both, right? That you can't just maximize on one and leave out the other, but you kind of have to find a way of balancing as you try to test and evaluate the models. Yeah.
Okay. Then I want to extend maybe a final or almost final topic that is more towards video and self-supervised learning. Recently, there have been a few papers. I seen that, like, for example, the best paper award at iClear, showing that we can now train self-supervisedly on video, get performance that is close to annotated data set of million of images, and this is quite exciting, right? I mean, Vicky, since you've been the one talking about video, what can you say about that? What's your feeling, and where the field is going with that, in your opinion? And maybe what could we do here on the continent? What can the people do? I mean, would that be interesting to have other data set around this?
I think generally working with lower levels of supervision is super interesting and super hard. So first of all, good luck to everybody that starts that. But more seriously, I think that that can be a very good alternative to manually annotating tons of data. So I guess there will be, like, for example, I don't know, like you want to do a topology of I don't know, a particular place in Africa of the landscape, like from remote sensing or from a drone that flies above, then in this case you could use self-supervision to try to do this segmentation. It's not going to be perfect, but perhaps it can be an initial step in order to start training models that are particular for Africa, either foundation models or actual models that can be applied like for downstream applications. So I would guess that like basically using self-supervision for this type of cases can only help, because it's another way of exploiting the data. And synthetic data maybe. Synthetic data also.
Synthetic data. Yeah, that's a good point. And I think probably if you go towards my feeling is no supervision can open the door for, okay, you have the bias of your data for sure. You have to control what you have in your data set. You have to be mindful about it much more than we've been for all those years. So I think now that people are discussing about this, it does feel that unsupervised can be a way to not care about annotation, that also bring another level of bias. And probably, in my opinion, there are so much things that can be done with just raw data. And so hopefully, I mean, the internet is full of data, and it's a matter of picking the right one and have the resources to train a few models, I guess. But yeah, it does feel like there is hope in that direction.
All right. Thanks a lot. Before closing, we caught up a bit on the delay. I want to put you on the grill. Just a few minutes, just all of you. You're the one on stage. One thing that is very, very hard for students is finding the right direction, the right topic, the right project to be working on. So I want to give you one sentence or two sentences to tell me, each of you, if you were in a condition of low resource computation, maybe also in condition where you cannot have access to all the data sets, you have the data space. I mean, currently in our world, right? You're working on the continent. What would be a project that you would advise? I know it's like, yeah, it's tough. Who want to start first? I feel Pierre-Luigi is ready to start.
I want to talk, of course I said before, emerging topics like the one I presented, so exploring fundamental problems with tiny networks. For example, the problem I was talking before, the random initialization of networks to train is a problem when training meta networks. And for this kind of study, actually, you don't need many resources. So this would be a project that maybe I could suggest if you don't have many resources. But if I want to also to suggest you something different in another my research topic, I think that among my projects, maybe supervised anomaly detection is also a topic that requires really a few unlabeled samples, and in some context, in multimodal context, there's still space, and you don't need so many resources to do that. So that would be, I think, another research that I would suggest.
So I carry on. It's the order. So the correct answer is that I do not know. My guess would be I would try to reverse the table if that was the case. So that would mean two things. One, more practical, transform problems to sub-problems that are solvable. For example, I want to do geographic understanding of, I'm using this example because one of you or two had these posters outside. Like instead of using vision to understand like geographic things, like transform everything to coordinates and try to do diffusion on the coordinates. So this is something that like basically is a transformation of the problem. The same can happen with data, like instead of using like visual data, again, let's say for the example of remote sensing, again, some of you had it outside, like translate it to textual data. So it's much faster to do textual data. And from textual data, like subsample, like do some of them, which are important, do some pre-processing to understand what's important. So basically it would be like reverse the problem, I mean, transform the problem to something that is a proxy problem, a sister problem, let's say, that you can very well solve that and say, well, like this works very well with limited data. Or do that and then go to somebody that you know have a lot of data or a lot of resources. So for example, check what Raul is working on and then work on a sister problem that Raul is working on and then go to him and say, hey, look, I did something very similar to you. Do you want to hire me now? And that can work also because then you solve your problem.
It's a hard one. It's a hard one, yeah, but I guess semi-supervised learning, I think we've had a master's student in the health who did that for breast cancer diagnosis. So, of course, we couldn't get all the data labeled because it's very difficult. She didn't have sufficient data, but she managed to do it with semi-supervised learning and get good performance. So I think that would be the approach. Don't go for a complex problem. I think start small is really what I would advise. If it's, for example, speech, maybe start small because you can't have all the data transcribed. That's very expensive if you wanted to do that for the multimodals, but you can start with a smaller problem and then see how that evolves to kind of build up the bigger problems. Again, it's a very complex question. Yeah.
Cool. I'll try to go fast. I'll say analysis of trained models, so evaluation. You can take existing data sets, see what happens if you swap out English for different languages. Let's say you swap it out for Yoruba, you swap it out for Swahili, what happens? And then number two, I would say connect with researchers at universities or labs with funding because you deserve the opportunities and they should want to support you.
I would say more than start small, start with one image. Start with one notebook, one image, spend time understanding what is happening on that. Then a second one, see if it generalizes. A third, but like really put your hand in it on the notebook. That's how most of my projects have started.
Amazing, I mean, amazing advice. I'm happy to get them for me as well. Thanks a lot. Let's give a round of applause to our speakers. Okay, you can stay on stage or not, up to you. But we're going to announce the award now. So I'm going to come back. Okay. Okay, you chose to stay on stage. That's perfect. All right. So, thanks to everyone that stayed up to the end, and to all the other, by the way. I understand also to be tired at the end of Indaba. It's quite intense. There's the screen, if we can, yeah. All right. So, awards. I know that you're waiting for that. That's why we put it at the end, to keep you there. We have 2 awards, 2 prizes, the best paper award and the best poster award. And at the end of these 2, there is a bit of a surprise, so stay around. And these are the 2 awards, and let's just thank real quick Snap and GoPro that has been supporting us. So thanks to both of them for providing the prize for the workshop. The first award that I will announce is the one of the Best Poster Award, winning a GoPro Hero 13, I think it is. You will get your prize, by the way, tomorrow, because we'll also announce again the award at the main Indaba ceremony, so that's a change, so we'll give you the prize tomorrow. And also to say that the 2 awards are almost the same value, so it was difficult to decide which one has which one. So the Best Poster Award is going to self-supervised learning for 3D kidney segmentation on contrast-enhanced computed tomography images. This is the work of Isen Brahimi. You can come. You can say hello to the speaker. Sure. Shake hand. Kudos to you. Let's do a round of applause again. All right, I'll go right away to the next one. The best paper award. We can do picture after, no worries. And you want to say one word?
So I was not expecting this at all. It's just a simple project, just a small part of my internship project that I participated with, just to gain feedback from experts here and other students. Valuable feedbacks are important for me and for my career. Like to improve and learn. So I'm speechless. Yeah, so thank you so much for this honor. Thank you so much. It's really motivating, and hopefully I will always keep it and remember it in my future projects. Okay, so thank you so much.
Super happy for you. You can stay around. We'll soon close. The second award that we're gonna give now is the Best Paper Award. This is a prize award, and it was almost missed by someone that left the room a bit before, and the awards goes to BioNAS, the Incorporating Bio-Inspired Learning Rules to Neural Architecture Search, and from Himan Azawi that is here. Almost missed, eh?
Well, actually, I almost missed the deadline, and I was wishing from my heart that she would receive the award, and I'm happy that we're together and we're from the same school. So thank you, everyone. Thank you for the sponsors and for the organizers of WSCV. And as the legend says, when you volunteer, the next year, you're going to win. Thank you.
Thank you, Iman, for saying it. It's true. We had the same last year. So the volunteer of this year, be ready. And the little twist is that we also, it's not the first time, but we also had troubles between the speakers because they were a lot of really cool work. And I know you put a lot of effort in the works, and we cannot reward everyone. But we wanted to reward also 2 other works. It's not only one, but it's 2 other works with honorable mention. to highlight also the amount of work that you have put, both doing practical experiments, sometimes recording data set, and at the same time also trying to achieve result with training models. So that being said, 2 other papers are being rewarded today. We don't have prize, but you have all our gratitude for that. So kudos to both the RGB UAV imagery segmentation comparative study from Matthew Jerry. Matthew is not around. Oh, yeah, okay, cool. Bravo, Matthew. A lot of work also recording data. And to the second paper, I'm going to say it right away, the crack detection in building using CNNs. This is a work from Yusuf Olani and all collaborators. So you can come on stage if you want to say a word quick, you can.
I'm just really excited. I didn't expect this. I'm really excited to mention the honorable mentions. Now I can confirm that my work is really progressing. Yeah, it's very hard work.
Hi everyone. Well, we were not expecting this, so I'm a bit, but yeah. This is just like a project that was inspired by the first person, Yusuf, because he's a civil engineering student, and we both just jumped on it because we believe that we can make a lot of impact in this field. But yeah, thank you for the encouragement. Now we know that we are doing something great, and we would not give up on it and continue to make sure that we complete the project. Sorry for my rushed speech, but yeah. Don't say anything. Yeah, thank you.
Bravo to you. So kudos to all of you. We have some plaque for you from custom handmade Goree Island. So you'll have them there. You can come and we can do picture. But I think it's time to close the workshop because there are other plans after. So thanks to all of you being there, the attendees. Thanks to all the people that submitted work, that presented work. It's a lot of work. We're completely aware of that. So I can see the level improving year after year. It's my 3rd year at Indaba. So kudos to all of you and a big round of applause for the participant, please. And with that, we close the workshop. I'm just reminding for you the existence of the African Computer Vision Summer School. You'll have all the details on the slides.